Hello there, and welcome. Tonight, we drift into a universe filled with quiet impossibilities and truths so strange they barely sound real. Astronomy is full of moments like that, stars that spin like whirlpools, planets made of crystallized carbon, oceans of light that pulse across the sky. Even the empty spaces between galaxies carry secrets that reshape the way we understand existence. As you settle in, let your thoughts loosen. You are about to wander through 100 surprising revelations waiting in the dark, each one stranger and softer than the last. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Astronomy has a way of loosening the edges of what we think is possible. When you step back from the familiar patterns of daylight and seasons and look instead at the wider stage where suns are born and galaxies drift, the universe begins to feel almost impossibly strange. Yet these strangenesses are not fantasies. They are real features of a cosmos that has been unfolding for billions of years, shaped by forces we can barely imagine. Astronomers spend their lives trying to make sense of this vastness, gathering clues from light so faint it has traveled across time to find us, and from motion so subtle they slip quietly through the night. Often, the first revelation comes from realizing how little of the universe we can see directly. Most of its wonders hide behind distance, dust, or silence. The glowing shapes we notice in the sky are just the brightest and closest hints of a reality far deeper than starlight. Through telescopes that catch everything from radio waves to gamma rays, astronomers reveal invisible storms, folded structures, and drifting objects that would otherwise remain unknown. Light becomes a messenger, carrying stories across emptiness, telling of past collisions, ancient explosions, and the quiet persistence of stars that burn for spans longer than life on Earth has existed. Some of the strangest truths emerge from watching light change as it travels. Starlight can stretch, bend, or split depending on what it passes by. When astronomers see the same star appear in slightly different places at once, they know the light has curved around a massive object, distorted by gravity itself. That bending of time and space, quiet and invisible, becomes a gateway to measuring objects too dark to see. Whole galaxies can be mapped by the way they warp the light behind them. Even the empty spaces between clusters reveal their hidden weight through distortions that ripple across images like faint fingerprints. In other cases, the universe reveals its secrets through motion. Stars wobble because unseen planets tug on them. Galaxies rotate at speeds that make no sense unless something more massive than their visible matter is holding them together. When astronomers noticed that the outer stars of galaxies moved almost as fast as those near the center, it opened a path toward understanding that most of the universe is made from something mysterious. This unknown matter cannot be touched, held, or seen, yet it surrounds everything, shaping the cosmic architecture. By studying these subtle motions, scientists uncover the presence of forces that remain entirely silent. The scale of astronomical discovery often feels unreal. Consider the moment when researchers first captured the faint trembling of space caused by distant collisions. These ripples were so small that detecting them meant noticing changes smaller than the width of an atom. Yet those tiny shifts carried news of black holes spiraling together far beyond our reach. Instruments on Earth felt the passing crest of gravitational waves that began their journey long before any recognizable life had formed here. Through these tremors, astronomers listened to events so powerful they reshape the very fabric of the cosmos. Sometimes the clues come from particles rather than light or motion. High-energy messengers streak through the galaxy and drift into detectors buried underground or under ice. These particles, nearly weightless and barely interactive, travel through planets and stars with ease. To catch even a few is to glimpse the hidden engines of the cosmos. They tell of reactions inside suns, of ancient explosions that scattered elements across space, and of extreme environments where matter is crushed into forms beyond ordinary comprehension. Each captured particle is a whisper from a distant moment, carrying the memory of its origin like a faint signature. Much of what astronomers learn comes from patterns that only become clear when thousands or millions of observations are combined. A single star may tell part of a story, but the motion of many stars reveals a structure. The brightness of one distant supernova may seem unremarkable, yet when compared with others, it becomes a ruler for measuring the expansion of the universe. By watching how galaxies drift apart, scientists discovered that expansion is not slowing down but speeding up, as if pushed by a force even more elusive than the matter we cannot see. This revelation reshaped cosmology, turning the empty spaces between galaxies into places of quiet acceleration. The tools used to uncover these truths are as varied as the mysteries themselves. Some telescopes soar above the atmosphere to collect light that would be blocked at the surface. Others sit in deserts, on mountaintops, or at the poles where the air is thin and the darkness deep. Still others use arrays spread across continents, linking signals in perfect synchrony to form instruments the size of the Earth. Each tool is designed to catch a different kind of emission because the universe speaks in many voices. Where visible light shows only a smooth shape, radio waves may reveal spirals, filaments, or hidden jets. Infrared light uncovers stars still wrapped in dust. X-rays highlight violent regions where matter tears itself apart. What makes these discoveries so extraordinary is not just the strangeness of the phenomena, but the quiet patience required to reveal them. Many of the signals astronomers study are barely above noise. Small variations measured over years or even decades. A slight shift in a star's rhythm might indicate a hidden companion. A faint curve in a distant galaxy's shape might hint at unseen mass. Even silence can be meaningful when it contradicts what theory predicts. The universe rarely announces its secrets. Instead, it leaves trails, slight deviations, and delicate impressions waiting for someone patient enough to follow them. As you listen to these truths, the strange becomes soothing. The cosmos is enormous, yes, but its behavior is governed by patterns that can be traced, measured, and understood. Astronomers work in a realm where time is long, distances are vast, and evidence accumulates slowly like dust settling on stone. Yet within that quiet, they unveil wonders that stretch belief, revealing a reality richer than the one we glimpse with the naked eye. The universe is not simply a collection of stars scattered across darkness. It is a living structure shaped by gravity, motion, light, and the silent weight of things we cannot see. Each discovery adds another layer to our understanding, widening the horizon of what is possible. And as we drift through these truths, guided by the patient work of those who study the night, we find ourselves part of a story far larger than our own. Stars often seem like the simplest objects in the night sky, steady points of light that rise and set without complaint. Yet when astronomers look closely, they find that many behave in ways so strange they almost feel like riddles. Some twist themselves into knots of magnetic fury. Some pulse like beating hearts. Others cool, collapse, flare, or split their outer layers with such force that whole regions of space glow from the shock. A star is not a static lamp suspended in darkness. It is a restless engine, always shifting, always in motion, shaped by pressures that could crush worlds and heat that could turn rock into vapor. And among these countless suns scattered through the galaxy, the strangest are the ones that refuse to follow the rules. There are stars that flicker with eerie rhythms, brightening and dimming in cycles so precise they feel almost alive. At first glance, the changes seem gentle, harmless, like a breath, but beneath that quiet pulse lies an entire internal world reshaping itself. As gases churn and collide in layers deeper than any ocean on Earth, shock waves ripple outward, expanding and contracting the star like a beating heart of light. The pattern can continue for centuries, each rise and fall a soft echo of forces working far below the surface. For astronomers, these stars become cosmic timekeepers. Their steady rhythms offer clues to their size, age, and inner structure, as if the star itself is whispering its secrets through the cadence of its glow. Other stars spin so quickly that their bodies flatten at the equator, stretched wide by their own momentum. Picture a sun turning fast enough that the centrifugal force lifts its outer layers outward, creating a shape that is more like an oblate sphere than a perfect circle. Some rotate so rapidly that their surfaces race around in just a few hours, creating intense magnetic fields that twist into loops and flares. These flares can be thousands of times more powerful than anything the sun can produce. A nearby planet caught in one of these storms would be stripped of its atmosphere in moments. Yet from afar, all we see is a flicker of brightness, a whisper of the unbelievable energy unfolding in silence. There are stars that grow colder and denser at the same time. As they age, their outer layers drift away, leaving behind a core packed so tightly that a single teaspoon of its material would outweigh mountains. These remnants glow softly with leftover heat, cooling over billions of years. In their youth, they may have been enormous, blazing giants. Now they linger as quiet embers, the preserved hearts of long-vanished suns. Some even crystallize over time, turning into vast cosmic diamonds drifting through the dark. No one alive will ever witness a full star cooling into complete darkness. The universe itself is not old enough yet. Some stars hide companions so close that the two circle one another in tight spirals. Their gravity locks them into a mutual grip, drawing them closer as they age. Eventually, one may begin stealing matter from the other, tugging gas away in streams that arc through space like glowing rivers. This theft can reshape both stars, altering their brightness and temperature, or triggering bursts of energy when the stolen gas piles too quickly onto the surface. In a few cases, the process becomes so unstable that the star erupts entirely, creating an explosion visible from thousands of light years away. When this happens, a single instant of fury can outshine whole galaxies. There are stars that vanish behind curtains of dust and then return again, their light dimmed by clouds drifting across their path. Some of these changes are simple eclipses, caused by large companions or rings of debris passing in front of the star. Others are far stranger, with irregular dips so deep and unpredictable that astronomers once wondered whether they were witnessing engineering on a cosmic scale. The truth is likely natural, shaped by enormous drifting structures of dust or the fragmented remains of comets. But the mystery of those strange dimming patterns remains a gentle reminder that the universe still guards more secrets than we have uncovered. Some stars are born in places so crowded that they feel gravitational tugs from every direction. In these dense clusters, stars can pass dangerously close to one another, exchanging energy in ways that alter their paths forever. A star might be flung outward at incredible speeds, hurled from its home, and set on a long, solitary journey through the galaxy. Others may collide outright, merging into a hotter, brighter star that looks far younger than its neighbors. To an astronomer, such a star is an impostor, a rejuvenated object hiding the truth of its ancient origin beneath a fresh, blue glow. There are stars that drift through interstellar space without a galaxy to call home. They roam the cosmic wilderness, far from the ordered spirals and clusters where most stars are born. Many were likely thrown out by the gravitational turmoil of galactic mergers or by violent interactions with black holes. Alone in the dark, they move without the company of nearby suns, without the familiar glow of a shared night sky. Their light still shines, faint and steady, even though no planet circles them and no nearby stars keep pace. One of the most astonishing behaviors belongs to stars that collapse into objects so dense that their magnetic fields become unimaginably strong. These stars can emit bursts of radiation that sweep across space like lighthouse beams, rotating in predictable intervals. The timing is so precise that they rival atomic clocks in their consistency. And yet these pulses originate from environments no machine built by human hands could survive. When their beams sweep across Earth, We detect them as regular flashes, each one a reminder of a spinning remnant from a long-ago explosion. Even more peculiar are stars whose magnetic fields twist so violently that they crack their own crusts. When this happens, the star releases a sudden surge of energy, sending out flares capable of lighting the surrounding space in a wash of high-energy light. These events last mere moments, but their intensity is staggering. Astronomers detect them as brief, powerful bursts, echoes of internal stresses that would tear any familiar material apart instantly. All these behaviors, from the rhythmic pulse of variable stars to the violent flares of magnetic giants, reveal a truth that often goes unnoticed when we look at the gentle glow of the night sky. A star is not a simple point of light. It is a story in constant motion, shaped by pressure, gravity, temperature, and time. Each one is a furnace, a laboratory, and a mystery. And as astronomers continue to study their rhythms, their collapses, their eruptions, and their fragile balances, they uncover new ways in which stars defy expectation. These impossible behaviors are not exceptions. They are part of the universe's language, written in light and motion, waiting patiently for anyone willing to look up and listen. When you imagine a planet, you might picture something familiar, shaped by sunlight, wrapped in air, and turning steadily through gentle seasons. But across the galaxy, worlds exist that feel more like riddles than destinations, each one testing the limits of matter, chemistry, and imagination. These are planets sculpted by blazing radiation, torn by tidal forces, drowned in storms, or locked in eternal twilight. Some shimmer with molten surfaces. Others are frozen so deeply that even starlight cannot soften them. A few harbor winds so fast that the atmosphere itself is whipped sideways in a constant roar. The universe is full of landscapes we were never taught to expect. There are planets that orbit so close to their stars that their day-sides glow like metal fresh from a forge. Heat on these worlds climbs high enough to vaporize stone. Mountains crumble, not from erosion, but from constant boiling, drifting into the upper atmosphere as mineral vapor. When the winds shift, that vapor cools and condenses, falling again as glittering droplets that form pebble rain. On some of these inferno worlds, the contrast between day and night is so severe that the surface on the shadowed side freezes while the day side burns with furnace intensity. The boundary between the two becomes a turbulent scar of storms roaring around the planet in a permanent ring of chaos. Some planets cling to orbits so tight that they show their star only one face forever. One hemisphere endures unending daylight, scorched without pause, while the opposite side sinks into blackness so deep that heat cannot cross the threshold. On these tidally locked worlds, the twilight zone between the bright and dark halves may be the only place where temperatures fall within any tolerable range. Imagine living in a world where the sun never sets, or a world where dawn never arrives, the horizon frozen in a permanent glow. Even the winds behave strangely here, racing from day to night in looping, spiraling currents driven by the planet's desperate attempt to balance itself. Then there are worlds made of materials so unexpected they feel like tricks of the imagination. Some are composed largely of carbon, buried under pressures fierce enough to turn that carbon into a vast crystalline mantle. Their surfaces may hold shimmering plains of compressed diamond beneath layers of darker rock. If such a world cracked open, it would reveal a glittering heart sculpted by forces that could never be replicated on Earth. Other planets have oceans of liquid metal glowing from internal heat, shifting like living mirrors in waves that stretch for hundreds of miles. To look upon one of these seas would be to stare into a molten horizon bound only by gravity. Not all extreme planets burn. Some freeze to degrees so profound that even the atmosphere collapses onto the ground as frost. On these icy worlds, the surface is a silent expanse where mountains rise from solidified gases and winds carry grains of frozen air. The faint, distant sun gives little warmth, leaving the planet locked in a darkness softer than velvet. Yet beneath this stillness, some of these frozen realms hide subsurface oceans, warmed by gravitational squeezing from nearby moons or gas giants. These hidden waters stretch beneath ice sheets thicker than continents. It is within darkness like this that life, if it exists, would move slowly, guided by chemical whispers instead of light. There are planets that orbit not one star but two or even three, tracing graceful loops through intertwined systems of light. On their surfaces, dawn may arrive with several suns rising together in soft colors, or one star might dip below the horizon, only for another to brighten the sky moments later. The patterns of illumination become a braided rhythm of shifting shadows and triple-tinted afternoons. Such worlds may have seasons so complex that no 2 years look alike. Their skies would never grow predictable. Their weather would answer not to a single sun, but to a celestial choreography unfolding above them. Some planets wander freely without any star at all. These drifting worlds roam the galaxy alone, cast off from their home systems by gravitational upheaval or born from collapsing gas clouds that never sparked into suns. Without the warmth of a parent star, their surfaces fall to unimaginable cold. Yet within their interiors, heat from formation or radioactive decay may still linger. If they carry thick atmospheres, those gases can trap warmth, creating dim, warm pockets under skies lit only by starlight too faint to cast shadows. To float across such a world would feel like walking under an eternal midnight, guided by the soft glow of distant galaxies. There are planets where storms never stop. Gas giants wrapped in bands of color from pole to pole often spin so rapidly that their atmospheres collapse into layers of jet streams, each flowing in a different direction. Storms swirl into vast spirals that could swallow Earth with ease. Lightning flashes across clouds of ammonia and ice, and winds howl at speeds that defy intuition. The deeper layers grow hotter and denser, collapsing gradually into metallic hydrogen so conductive that it creates magnetic fields stronger than any found on terrestrial worlds. These interiors churn in patterns that are still not fully understood, shaping storms that persist for centuries. A few planets orbit stars so violent that flares strip away their atmospheres piece by piece. Over time, these worlds transform from lush spheres of gas into scorched rocky cores, stripped bare by constant radiation. Others begin as rocky planets but grow thick envelopes of gas as they age, becoming something between a terrestrial world and a gas giant. The boundaries blur, the definitions soften. What counts as a planet becomes harder to pin down. Some worlds defy simple classification entirely, challenging astronomers to expand their understanding of how celestial bodies grow and change across billions of years. There are planets with glass storms that blow sideways in supersonic winds. The sky on these worlds glitters with shards carried by turbulent gusts that race from the heated dayside to the cooler night. Some planets rain molten iron, others rain methane. On certain frozen moons, jets of water burst from the surface like geysers, spraying into space in arcs that fall back as delicate frost. Across the galaxy, atmospheres and surfaces weave together in combinations that seem almost unreal. Yet each follows the same physical laws, sculpted by gravity, temperature, and time. Taken together, these worlds form a cosmic gallery of the extraordinary. They reveal that planets are not quiet spheres circling politely around stars, but dynamic environments shaped by extremes beyond human experience. They burn, freeze, whirl, stretch, collapse, and endure. They rewrite the borders of what a planet can be, reminding us that the universe is not obligated to match our expectations. It grows stranger and more beautiful the deeper we look, offering landscapes that challenge imagination and truths that shimmer just beyond the reach of familiar thought. Galaxies often look serene from a distance, like soft spirals or hazy ovals pinned against darkness. Their curves seem smooth, their light steady, their shapes timeless. But when astronomers study them closely, they find stories written in distortion and debris. A galaxy is not a peaceful island of stars. It is a survivor, shaped by collisions so vast they unfold over hundreds of millions of years. slow enough to appear still, yet powerful enough to reshape entire regions of space. Every graceful arc and faint ribbon of starlight carries the memory of something that once drifted too close. When two galaxies begin to approach, they sense one another long before they touch. Gravity reaches out like an invisible tide, tugging on stars, bending orbits, and stretching gas into faint wisps. From afar, this early stage looks delicate, almost tender, but the forces involved are enormous. Stars are drawn into long loops that wrap around the galaxies, like ribbons pulled from a spool. Great plumes of dust surge outward, illuminated by newborn stars formed as clouds collapse under the strain. Even galaxies that appear undisturbed may hide these faint structures within their halos, the lingering traces of ancient encounters long forgotten. As the galaxies continue their slow spiral toward one another, their shapes begin to warp. The disks bend and twist. Arms stretch until they form bridges between the merging bodies. What once looked like two distinct islands begins to resemble a single, distorted form, stretched thin in places and swollen in others. Stars rarely collide directly. The spaces between them are too vast. Instead, the real turbulence occurs among the gas and dust nests where stars are born. Shock waves ripple through these clouds, compressing them into bursts of star formation that flare blue and bright. Whole constellations ignite in the wake of gravitational upheaval. Sometimes the collisions are gentle, with a small galaxy passing through a larger one like a stone dropped into water. The smaller object may be shredded, its stars scattered along long arcs that circle the host galaxy. These stellar streams can persist for billions of years, faint trails that reveal the path of the vanished companion. Astronomers search for these streams the way archaeologists search for ruins, tracing the curvature of the strands to reconstruct the orbits of galaxies that no longer exist as independent entities. In this way, the outer reaches of a galaxy become a kind of cosmic archive, each arc a record of an encounter written across time. Other collisions are far more violent. When two large galaxies meet head-on, their centers plunge into one another and their gas clouds crash together. For a brief cosmic moment, the entire system becomes a storm of creation and destruction. Massive stars form in waves, burning brilliantly, and then dying quickly in explosions that enrich the surrounding space with heavy elements. These supernova carve cavities and send shock fronts racing outward. Over time, the chaos settles, the stars adjust to new orbits, and the merged system begins to relax into a new shape, often an elliptical galaxy, with a smooth glow and a deep central core. Some galaxies reveal the aftermath of these interactions through strange asymmetries. One side might be thicker than the other, as if pulled downward by an ancient visitor. Another might show a bent disk or a warped halo. Dust lanes twist in unexpected angles. Streams of stars wrap like ghostly scarves around the main body. These features do not fit the classic textbook diagrams. They arise from the messy, unpredictable nature of cosmic encounters. Each anomaly is a clue, a fossil of motion left over from moments when galaxies collided, scraped, or brushed past one another. There are galaxies with rings that encircle their centers, created when a smaller galaxy punched straight through the disk of a larger one. The impact sends ripples outward, shaping waves that travel through the stars like circular shock fronts. As these waves expand, they compress gas into arcs of bright new suns. To see such a galaxy is to witness the echo of an impact frozen in time. The ring will continue to expand until it fades into the surrounding space, but for now it shines like a delicate ripple left on the surface of a cosmic pond. Other galaxies contain long tails that stretch tens of thousands of light years into emptiness. These tails are composed of stars torn free during close encounters. They drift along paths carved by gravity, often curling back toward the host in graceful loops. Some tails feed material inward, fueling central starbursts or feeding supermassive black holes hidden within the core. Others drift outward forever, thin and pale but still bound by the memory of the collision that formed them. Even galaxies that live in quieter regions of the universe cannot escape the influence of their neighbors. Tiny companions orbit them like moons, spiraling slowly inward as tidal forces pull them apart. Over time, these small galaxies dissolve into streams and shells, adding their stars to the outer halo of the larger system. The halo becomes a patchwork of generations, each layer built from the remains of smaller galaxies consumed long ago. When astronomers map these structures, they see not a single unified object, but a mosaic stitched together over billions of years. The most astonishing truth is that the universe itself encourages these encounters. Galaxies are not isolated. They travel in groups, drawn together by shared gravity. The spaces between them are vast, yet not empty. Motion and attraction weave them closer over cosmic timescales. Given enough time, most galaxies will either merge with neighbors or be shaped by their influence. Even our own galaxy is not exempt. The Milky Way carries signs of past collisions in its halo, its streams, and its warped outer disk. And far away, drifting closer each moment, Andromeda waits. In the end, the shapes we see when we look at galaxies are snapshots, single frames in a long unfolding story. Spirals, rings, shells, and tails are all temporary. They rise, ripple, fade, and reform. Collisions sculpt them. Encounters stretch them. Quiet catastrophes reshape them from within. To watch galaxies is to watch change measured across spans longer than civilizations. And yet, within this slow dance, there is beauty in every distortion, every echo, every faint arc of stars swept into the dark. The universe is shaped not only by what we can see, but by what we cannot. It moves under the influence of forces that leave no direct mark on our eyes, yet guide the paths of stars, bend the arcs of galaxies, and weave the large-scale structure of space itself. These invisible influences do not glow or shimmer. They offer no color or contour, but their fingerprints are everywhere, written into motions that would make no sense without them. Astronomers learned long ago that the cosmos does not obey only the pull of visible matter. Something deeper, quieter, and more pervasive shapes the world beyond starlight. One of the most mysterious of these influences reveals itself in the way galaxies rotate. If only the stars and gas we can see were responsible for their motion, the outer regions would drift more slowly, easing around the center in wide, relaxed loops. Yet when astronomers measure their speed, they find something astonishing. Stars far from the core race around almost as quickly as those near the center, as if held tightly by a force we cannot see. The visible galaxy alone cannot account for this. Something unseen, something massive, surrounds and permeates these structures. This hidden substance has become known as dark matter, a presence that outweighs all luminous matter many times over. Though it cannot be touched or detected directly, its gravity binds galaxies together, keeps clusters from flying apart, and shapes the cosmic web that stretches across the universe. Dark matter does not clump like ordinary matter. It forms vast halos around galaxies, smooth in their outer regions, denser toward the center, and extending far beyond the reach of starlight. Within these halos, galaxies drift like lanterns suspended in invisible scaffolding. In the early universe, dark matter gathered first, forming the seeds where gas later pooled and ignited into stars. In this sense, everything we see today grew around an unseen skeleton, shaped by a force that whispers rather than shines. The universe is built on a foundation we cannot touch, yet one that holds the architecture of everything familiar. Another invisible force shapes reality on an even deeper level. Gravity itself, though described by its pull, is not a material thing. It is a bending of space and time, a curvature caused by mass. Where matter gathers, space folds. Where space folds, motion changes. Light follows these curves even though it has no weight, and so starlight bends around galaxies and clusters, revealing the shape of gravity's influence. Sometimes a distant star or galaxy appears, stretched or multiplied, its image distorted into arcs or rings. These shapes are not optical illusions, but the result of space itself being warped. Through these distortions, astronomers glimpse places so distant their light began traveling before the Earth formed, all thanks to a force that cannot be seen yet acts on everything that exists. Even more elusive is the force that seems to accelerate the expansion of the universe. When astronomers began measuring distant supernova in the late 1990s, they expected to find that the universe was slowing down, pulled inward by its own gravity. Instead, they found the opposite. Galaxies far away were receding faster than expected, as if pushed by a gentle but persistent pressure. This phenomenon, now called dark energy, fills space like a quiet tide, urging the cosmos to expand ever faster. No one knows its true nature. It may be an energy of space itself, or something woven into the fabric of existence that we have yet to understand. But whatever it is, it shapes the destiny of everything, dictating how galaxies drift apart and how the universe will evolve far into the future. Magnetic fields, often overlooked, exert their own invisible influence across galaxies. Vast magnetic lines thread through gas and dust, shaping the flow of charged particles and guiding the motion of cosmic rays. These fields arise from the motion of plasma, twisting and folding over immense distances. Though weak by earthly standards, their reach is enormous, stretching across tens of thousands of light years. They sculpt the arms of spiral galaxies, influence how gas collapses into stars, and create structures seen only in radio wavelengths. In the space between stars, magnetic fields weave through clouds like unseen currents, pushing and pulling material into patterns that shape the birthplaces of new suns. Even on the scale of stars and planets, magnetic forces hold power. The sun's magnetic field erupts in flares and storms that travel outward, brushing past planets and shaping their atmospheres. In distant systems, stars with tangled magnetic loops release bursts of radiation so intense they can strip away entire atmospheres from unlucky planets. These invisible threads of magnetism stretch, snap, and reconnect in cycles that carry both creative and destructive potential. Though silent, they leave trails across space in arcs of charged particles and shifting winds. There are also forces born from motion itself. When massive objects collide or spiral toward one another, they send out ripples in the fabric of space. These gravitational waves stretch and compress reality as they pass, though by amounts far too small for ordinary senses to notice. For most of history, they remained purely theoretical, predicted by equations but never observed. Then detectors on Earth felt their subtle tremors, catching the faint echoes of black holes merging billions of years ago. The waves traveled across unimaginable distance, passing through galaxies, halos of dark matter, and the void between clusters, until they reached our world and gently moved the mirrors of a waiting instrument. They carried with them the story of a moment of unimaginable violence, yet the waves themselves arrived as the softest whisper. Electromagnetic radiation, though familiar as light, extends into realms we cannot see. Radio waves slide gently through dust clouds that block visible light. Infrared reveals warm regions hidden behind curtains of gas. X-rays and gamma rays expose violent regions where matter is torn apart or crushed into extreme states. These forms of light are not forces in the traditional sense, yet they act as messengers for processes that would otherwise remain concealed. They shape our understanding of the cosmos, guiding telescopes to regions where invisible forces are at work. Taken together, these unseen influences form the true structure of reality. They guide stars along their paths, decide the fate of galaxies, and determine how the universe expands. They do not glow. They do not shimmer. They simply act, quietly and steadily, shaping the cosmos from behind the scenes. Without them, galaxies would unravel, stars would not form, and the universe would be an empty, dark, without structure or motion. The beauty we see when we look into the night sky is only the surface of a deeper, hidden world, sculpted by forces that expect nothing yet give shape to everything. Light is often treated as something simple, a gentle brightness that reveals the world around us. But in the cosmos, light becomes a traveler, a messenger born in distant furnaces, carrying with it the memory of where it has been. Every shimmer in the night sky is a story that began long before Earth had oceans or continents, long before the first breath of any creature stirred the air. When you look at a star, you are not seeing it as it is now, but as it once was. The glow reaching your eyes tonight may have begun its journey when early galaxies were still learning how to spiral, or when the young universe was filled with gas clouds drifting through a darkness untouched by planets or life. Light does not arrive quietly. It arrives with history folded into its color and shape, a whisper from an older time. Much of the light we see began in the hearts of stars where pressure is so intense that atoms fuse, releasing energy that struggles outward through dense layers of gas. The journey from a star's core to its surface can take longer than the existence of entire civilizations. Photons bounce and scatter through tangled paths, losing their identity again and again as they collide with particles. By the time they escape into open space, they have already lived many lives, reshaped countless times, and still, their greatest journey lies ahead. Across years, across millions of years, they travel unbroken until they meet an eye or a telescope capable of receiving them. In that moment, the photon's long wandering ends, and the story it has carried for ages becomes ours to read. Some light is so old that it predates the formation of the Milky Way. It comes from galaxies so distant that their glow began when the universe was barely formed. This ancient radiance has stretched as space itself expanded, its colors sliding into deeper reds until only sensitive instruments can detect it. When astronomers capture this faint, reddened light, they are looking back toward a time when the first stars were still igniting, when the cosmos was finding its shape. To study these beams of ancient fire is to witness the universe's childhood preserved in motion. Other light originates in violent places, where matter falls toward black holes and heats to temperatures beyond comprehension. These regions release bursts of energy that race across the universe, flashing in waves invisible to the human eye. When these signals arrive at Earth, they reveal events that unfolded in realms we can scarcely imagine. Collapsing stars, magnetic fields twisted into knots, jets of particles hurled outward at nearly the speed of light. The brightness we detect today is the final echo of catastrophes that ended long before our planet formed. And yet the message survives, faint but persistent, traveling across the dark without ever slowing down. Some light slips through thick curtains of dust that block visible wavelengths. In infrared, these hidden regions glow like ember cores, revealing the birthplaces of stars. To peer into these nurseries is to see light that is woven through clouds of gas so cold that they might as well be frozen. When emerging stars ignite, they warm the dust around them, and the heat radiates outward in long waves that drift silently through space. These waves carry the earliest stories of stellar childhood, fragile and delicate, protected for ages until they reach telescopes tuned to notice their soft warmth. In these gentle glows, astronomers find clues about how stars take shape, how planets form around them, and how entire solar systems begin. Even the light that seems ordinary carries history. Starlight arriving from familiar constellations may have begun shining across space when human cultures were young, when ancient observers traced shapes into the sky that still guide our imagination. Every night, those same stars send new waves of light toward us, while the old waves continue traveling beyond Earth, passing other stars and drifting into deeper darkness. In this sense, light becomes a kind of cosmic rhythm. It ties the present to the past, reminding us that what we see is always a memory, never a moment. There are also forms of light that humans cannot detect without help. Radio waves stretch across space like long, drifting threads. X-rays reveal pockets of violence from blazing remnants of dead stars. Ultraviolet light marks regions where gases glow under fierce radiation. All these wavelengths move together through the universe, crossing unimaginable distances in silent unity. Each carries a different chapter of a story too large for any single sense to understand. When astronomers combine them, they begin to see the full complexity of galaxies, nebulae, and clusters, layered together like the colors of a painting revealed only under different kinds of illumination. Light interacts with gravity as it travels. When it passes near massive objects, its path bends, curving as though space itself is shaped like a lens. This bending creates arcs and rings that appear stretched or distorted when we observe them. These distortions allow astronomers to map the distribution of mass in the universe, including the hidden mass of dark matter. In a way, light becomes a sculptor's tool, tracing the contours of forces we cannot see directly. By following its curves, we learn the outlines of invisible structures that stretch across the cosmos like silent frameworks. Some light flickers in ways that reveal its origin. When a distant star brightens for a moment, it might be because an object has passed in front of it, bending the light through gravitational lensing. The flicker is brief, but the information it carries is profound. It tells of planets wandering around distant suns, or of compact objects hidden in remote regions of the galaxy. Each tiny change in brightness becomes a clue to something else moving in the dark, something we might never know existed if not for the way it briefly shaped the passing glow. And then there is the oldest light of all, a faint and uniform glow that fills every corner of space. This ancient radiation is a relic of the early universe, the cooling breath left over from a time when everything was dense and hot. It carries tiny variations that reveal how matter first clustered, how structure began to form, and how the universe has expanded through time. To measure this light is to listen to the quietest echo of creation, a whisper that has crossed nearly all of time to reach us. Light is more than illumination. It is a record, a traveler, a memory that endures across distances and ages. Every beam that reaches us has survived a journey so immense that even words like long and far cannot fully contain it. When you look at the night sky, you are seeing not just stars, but time in motion, history streaming toward you from all directions. The darkness between the stars may seem empty, yet it is filled with light still on its way. Stories not yet told. Messages from moments older than any world we know. Space is often imagined as a vast emptiness, a quiet stage where stars drift and planets orbit in predictable, graceful paths. But the deeper you look, the more you realize that the cosmos is filled with phenomena that twist the very fabric of reality. Space bends. Time stretches. Motion curves in ways that defy intuition. The universe is not a still canvas, but a living landscape shaped by forces that can fold, ripple, and stretch the dimensions themselves. What seems like emptiness becomes a medium through which strange events travel, leaving behind distortions that reveal their presence only to those who know how to listen. Some of the most dramatic distortions begin with objects so dense that their gravity becomes almost unfathomable. Black holes, formed from the collapse of massive stars, create regions where space is pulled inward with such intensity that nothing, not even light, can escape. Around them, space behaves like a whirlpool, twisting everything that comes too close into spiraling paths. Stars caught in their grip speed through arcs that defy ordinary motion, whipping around the black hole in tight loops before drifting back into calmer orbits. From afar, these motions look smooth, but up close, they reveal gravitational extremes that stretch understanding. A single orbit can carry with it the faint imprint of space-time curving in on itself. Near a black hole, even time loses its consistency. Clocks tick slower in the intense gravitational field, each moment stretched compared to regions farther away. If you could watch from a safe distance, an object falling toward a black hole would appear to slow, its motion becoming more languid as the space around it bends. To the object itself, though, the fall would feel swift, drawn inward by a force that grows stronger with every passing second. This separation of perspectives, born from curved space-time, reveals one of the universe's deepest truths. Time is not universal. It shifts and stretches depending on where you are, shaped by gravity just as surely as any orbit. Not all distortions require darkness. Some are born from light itself. When a massive object sits between Earth and a distant source of illumination, the light bends around it, creating arcs or mirrored images. This phenomenon, known as gravitational lensing, turns galaxies into natural magnifying glasses. Through these cosmic lenses, astronomers see objects far too faint or distant to observe directly, amplified by the curvature of space. Sometimes a single galaxy appears stretched into long, sweeping arcs. Other times, it forms rings of light, brilliant circles created by perfect alignment. These shapes are not tricks of glass or mirrors, but expressions of gravity sculpting the path that light must follow. Even stars can cause subtle versions of this effect. When a star passes in front of another from our point of view, the background star brightens briefly as its light bends around the foreground object. These tiny flickers reveal planets, compact remnants, or wandering bodies that would otherwise remain unknown. Each flicker is a small distortion in the fabric of space, a delicate bending that travels across years before arriving at a telescope capable of noticing it. There are also ripples in space-time that travel across the universe, like waves on a vast ocean. These gravitational waves form when massive objects accelerate violently, such as when two black holes spiral together and finally merge. The collision sends out pulses that stretch and compress space as they move. For ages, these waves were predicted but never confirmed, too faint for any instrument to detect. Then, one quiet moment, observatories sensed a tiny tremor, a movement so small it was less than the width of a proton. That tremor carried with it the final heartbeats of two merging black holes that collided long before humans existed. The waves traveled across an unfathomable distance, passing through galaxies and voids, and reached Earth as a fleeting whisper of distortion. Space can also twist under the influence of rotation. When a massive object spins, it drags space-time around with it, a phenomenon known as frame dragging. Near rapidly rotating black holes, space is twisted into spirals, forcing anything nearby to orbit in the direction of the spin. Even light must flow with the rotation, unable to resist the pulling of space-time itself. This twisting creates regions where motion becomes impossible to oppose, where the only possible paths are those demanded by the rotating fabric of reality. In these regions, the universe feels alive, as if the flow of space has become a river with currents too powerful to escape. There are stranger phenomena still, created by intense magnetic fields or the collapse of matter into compact forms. Neutron stars, remnants of massive suns, pack more mass than the entire visible surface of Earth into a sphere barely larger than a city. Their gravity is fierce, but their magnetic fields are even more extreme, stretching millions of miles into space. These fields twist particles into spiraling paths, creating beams of radiation that sweep through space like lighthouse signals. When these beams cross Earth, we see regular flashes that reveal the star's rotation. Underneath the rhythm lies a deeper structure, shaped by magnetic forces so strong they bend the behavior of matter and light alike. Even the motion of galaxies reveals distortions that originate from the structure of space itself. Clusters of galaxies drift together in vast formations, guided by filaments of dark matter, invisible threads that create a cosmic web. These clusters move in ways that defy simple gravity, accelerating or slowing depending on the distribution of this unseen mass. The motions act like currents in an ocean too large to map fully, carrying galaxies along pathways determined by forces that began shaping the universe long before stars formed. In certain rare regions, space-time becomes so curved that motion takes on unfamiliar forms. Orbits wobble, paths precess, light circles around objects multiple times before escaping. Even empty regions can contain distortion left behind from long-vanished events. Space remembers the forces that shaped it, holding residual curves and stretches like faint scars of ancient interactions. These traces remain for billions of years, reminders that even emptiness has structure. To look at the universe through the lens of these phenomena is to realize that reality is far more flexible than it seems. Space bends, time shifts, motion curves along paths, not set by choice, but by the shape of space-time itself. The cosmos is not simply a stage on which events unfold. It is an active participant, constantly shaped by the forces within it, and every distortion, no matter how subtle or spectacular, tells a story of energy and mass woven into the deep fabric of existence. In the vastness of the universe, there are places where silence is not just the absence of sound, but the expression of physical laws shifted into unfamiliar shapes. These regions often lie far from the warmth of stars, tucked between drifting clouds or deep within collapsed remnants where ordinary rules begin to fray. They are not empty, but subdued. Matter moves differently there, slower or faster than expected, drawn into patterns that seem detached from the familiar world. Even light takes on strange behaviors, dimming or bending in ways that reveal hidden structures. These are the quiet corners of the cosmos, where extremes create landscapes of stillness. One such region appears within the depths of molecular clouds. These clouds look like dark smudges against the starry sky, patches where light cannot pass. Inside them, the temperature falls so low that atoms move with reluctance, drifting through frozen darkness at speeds that feel glacial compared to the restless dance of warmer gas. Here, chemistry becomes delicate. Molecules form and break in slow motion, guided by faint traces of radiation from faraway stars. Each reaction is a whisper, so quiet and rare that entire lifetimes could pass unnoticed within the cloud's cold interior. And yet, from these silent depths come the first seeds of future suns, slowly gathering in pockets where gravity begins to tighten its grip. Far more extreme are the regions surrounding neutron stars, where matter behaves in almost unrecognizable ways. These stars compress more mass than the sun into a sphere barely the size of a city. Inside, atoms collapse, electrons fuse with protons, and matter becomes a dense ocean of neutrons packed so tightly that a teaspoon would outweigh mountains. The surface hums with magnetic fields so powerful they distort the behavior of atoms, forcing them into shapes no laboratory on Earth can reproduce. Space around these stars grows eerily still, as if motion resists entering the magnetic grip. Particles caught in that grip glide along rigid paths, trapped in arcs that loop around the star like frozen ribbons of light. Even radiation behaves differently, emerging in bursts that flash across space like faint pulses from a cosmic heartbeat. Then there are the silent interiors of brown dwarfs, objects that hover between the definition of a star and a planet. Too small to ignite sustained fusion, yet too massive to be ordinary worlds, they glow faintly with residual heat left from their formation. Deep within, pressures rise high enough to create a form of matter known as degenerate gas, where particles no longer move freely but press against one another like crowded dancers unable to step aside. This strange material resists compression not because of temperature but because of quantum rules that govern how particles occupy space. The effect gives the brown dwarf an eerie stability, allowing it to hang in limbo between fire and darkness for billions of years. Even quieter realms stretch between galaxies, in the immense voids where few stars shine, and the density of matter drops to almost nothing. These regions seem empty, yet they still carry the faint signatures of ancient expansion, leftover ripples from the earliest epochs of the universe. Hydrogen atoms drift here in isolation, separated by distances so vast that they could travel for years without encountering another particle. The silence in these cosmic deserts is profound, a silence not merely of sound but of interaction itself. Forces weaken, motion loses urgency. The void holds its breath for ages. Closer to home, within planets and moons, silence takes on different forms. Deep inside icy bodies that drift in the outer reaches of star systems, matter becomes so cold that crystals form intricate lattices under crushing pressure. Some moons hide oceans beneath thick shells of ice, where warmth from tidal flexing or radioactive decay stirs water in slow currents. In these subsurface oceans, minerals dissolve and settle in sluggish patterns, altering the chemistry in ways that reflect a delicate balance between pressure, heat, and time. These hidden seas are worlds unto themselves, silent laboratories where reactions unfold in the absence of sunlight, governed instead by the inner heat of a distant moon. There are regions where silence becomes a byproduct of gravity itself. Near black holes, the space just outside the event horizon is so warped that matter approaching it stretches into thin, elongated shapes. As it spirals inward, light emitted from the falling matter becomes increasingly redshifted, its energy sapped by the intensity of gravity. Observers from afar would see the infalling matter fade and dim until it seems to freeze in place, suspended in a perpetual moment. The silence here is not peaceful. It is a silence of halted motion, of time slowed by the weight of gravity. Quantum realms offer a silence of another kind. In the vacuum between particles, fluctuations appear and vanish too quickly for any traditional measurement to capture. This vacuum is not empty but filled with virtual particles that flicker into existence and then annihilate. Their presence shapes fields and forces in subtle ways, altering the behavior of real particles that pass through. These fleeting appearances do not create sound or light, yet they leave behind measurable effects that hint at a restless, unseen activity beneath the stillness. Inside the cores of giant planets, matter takes on unusual forms that cannot exist under ordinary conditions. Hydrogen, normally a gas, becomes metallic under extreme pressure. In this strange state, it conducts electricity and flows like a liquid metal, generating magnetic fields that extend far into space. This metallic hydrogen does not behave like anything familiar on Earth. It moves in slow, powerful currents shaped by heat and rotation. The silence here is heavy, as if the material carries memory of the immense forces that forged it. In the early universe, long before stars existed, silence dominated the cosmos. Matter was a warm, uniform fog of particles drifting through an expanding landscape. As the universe cooled, this fog shifted, forming delicate ripples that would eventually grow into the first galaxies. But before structure emerged, before light could travel freely, the cosmos was filled with a silence deeper than anything that exists today. It was a silence of possibility, where matter waited for gravity to sculpt its future. Silence in the cosmos is not emptiness, it is transformation. It is matter pushed to extremes that reveal new rules. It is the slow choreography of particles in the coldest depths and the frozen stillness near the densest objects. In these quiet places, the universe shows its capacity for strangeness, allowing matter to behave in ways that feel unfamiliar, ancient, or extraordinary. And though we may never stand within these regions, their stories drift through space, carried by light, gravity, and the subtle motions of a universe still full of secrets. Long before galaxies took shape, before stars lit the darkness, the universe was a warm sea of particles drifting through an expanding void. Most of that primordial era has vanished, washed away by time, gravity, and the birth of structure. Yet scattered across the cosmos are relics that still carry whispers from those earliest ages. They drift in the quiet outskirts of galaxies, burn softly in remote halos, or glide through interstellar space unchanged for longer than any star has existed. They are the fossils of creation, holding memories from a time when the universe was young and unsteady, learning how to become what we now see. One of the most ancient relics lies in the oldest stars themselves. High above the crowded disks of galaxies, faint suns wander through elongated orbits, their light thin and quiet. These stars contain almost no heavy elements, their atmospheres still carrying the near-pristine mix of hydrogen and helium forged after the first great flash of existence. They burn with a subdued glow, not because they are weak, but because they come from an era before the cosmos had been enriched by generations of stellar alchemy. To observe them is to look back across nearly the entire history of everything. Their chemistry preserves the signatures of the universe's earliest breaths, formed when galaxies were still mere clouds drifting toward the first hints of structure. Some of these stars are so old that their compositions feel almost alien. A few contain only trace amounts of heavier elements, proportions so small they challenge our understanding of how stars can ignite at all. They may represent the second generation born after the first colossal suns died in brilliant explosions. Those first suns, enormous and short-lived, created the universe's earliest metals, seeding the cosmos with faint dust that the next stars inherited. The relic stars we observe today carry those faint traces like whispers in their atmospheres. By studying them, astronomers unravel stories from times far older than any galaxy's spiral arms. Other relics drift unseen in the quiet spaces between stars. Tiny grains of ancient dust, forged in the atmospheres of long-dead giants or in the shock waves of the earliest supernova, survive as microscopic travelers. These grains wander for ages, sometimes finding their way into new stellar nurseries or embedding themselves within forming planets. Some even fall onto the surfaces of worlds like Earth, preserved in meteorites that descend through the atmosphere as blazing fragments of deep time. When examined, these grains reveal isotopes and patterns shaped in the universe's infancy, a chemical record written long before our planet existed. Meteorites themselves often hold relics even older than their parent stars. Within certain stones are inclusions that carry the signatures of early cosmic processes, tiny specks that survived the violent mixing of material during planet formation. They preserve a memory of the swirling disk of gas and dust that once surrounded the young sun, which was in turn shaped by ancient remnants drifting in from earlier generations of stars. Holding such a fragment is like touching a chapter from the prologue of the universe, a piece of history so old it predates the world beneath your feet. Even the cosmic microwave background is a relic, though it is made not of matter, but of ancient light. This faint glow fills the universe in every direction, the cooled echo of a once blinding radiance released when the cosmos was still opaque. Before this moment, matter and light were tangled in a hot, dense fog. When the universe expanded and cooled enough for atoms to form, light finally broke free and began its journey across time. That light still travels today, stretched into soft microwaves by the expansion of space. It carries with it subtle variations, ripples that reveal the earliest seeds of structure. From these patterns, astronomers reconstruct a time when no stars yet shone, when the universe was only beginning to shape itself. There are also relics hidden within the vast halos surrounding galaxies. These halos hold clusters of stars so ancient they formed before the main disks of galaxies fully assembled. Globular clusters, dense spheres of aging suns, orbit like quiet satellites. Their stars are some of the oldest known, packed tightly together yet glowing gently with a kind of enduring patience. Each cluster is a preserved fragment of an era when galaxies were still gathering their strength, when the cosmic landscape was shaped by small, fragmented structures merging into larger ones. They are survivors of a time when the universe was far more chaotic, and their continued existence offers a window into conditions long gone. Some relics are not stars or dust, but neutrinos, ghostly particles that rarely interact with anything. A faint background of these primordial neutrinos drifts through the cosmos, relics from the universe's earliest seconds. They pass through planets, stars, and galaxies with little resistance, carrying with them a record of energies and densities that existed before even the oldest light. Though nearly impossible to detect, they form a silent archive of the universe's infancy, moving continuously through space like ancient messengers that cannot be stopped. Even dark matter may carry relic information from the earliest ages, though we cannot yet read its story. The shape of galaxies, the speed of their rotation, and the clustering of cosmic structures all whisper of processes that began before atoms existed. Dark matter formed a scaffolding across which ordinary matter gathered, and that scaffolding still holds the imprint of the universe's earliest forces. It is a silent architecture, ancient and mysterious. Every one of these relics, stars, dust, clusters, light, and unseen particles, contributes to a deeper understanding of how everything began. They remind us that the universe is not only a place of change, but also a keeper of memories, carrying forward traces of events so distant they cannot be fully imagined. And as astronomers continue to listen, measuring light and decoding signatures hidden in the faintest particles, The ancient ages of the cosmos reveal themselves piece by piece, like echoes from a time before time had meaning. Across the universe, storms unfold on scales that dwarf any weather found on a world like Earth. They churn in silence through the vacuum, shaping magnetic fields, stripping atmospheres, igniting sudden floods of radiation, and sending shock waves rolling across light years. Though space carries no sound, these storms have presence. They flare with a violence that can rewrite the histories of planets and stars. They are eruptions born from magnetic tension, tidal strain, and the restless heat of cosmic furnaces. Wherever light shines, storms are waiting beneath the surface. Consider a star in its quiet phase, burning with steady luminosity that seems eternal to those who orbit it. Beneath that calm glow, tangled magnetic fields writhe and twist in layers of plasma that never stop moving. When those fields snap, reconnect, or fold under their own tension, they release bursts of energy so intense that the star brightens suddenly, flinging radiation far into space. These stellar flares erupt in arcs that rise and fall with exquisite speed, carrying charged particles outward in waves that move faster than any earthly storm. To witness such an eruption from afar is to see a star sigh with sudden force, scattering its inner heat into the surrounding dark. Some stars produce flares so powerful they rival entire galaxies in brightness for a brief moment. Magnetars, the most magnetic objects known, can release sudden bursts of gamma radiation when their crusts crack under magnetic stress. These cracks are not gentle shifts but catastrophic ruptures that send ripples through space, distorting particles and fields along their paths. The energy released in a single flare from a magnetar could strip the atmospheres of nearby worlds or ignite auroras visible across unimaginable distances. Yet these storms last only moments, brief flashes of power released from stars that spend most of their lives in deep, steady quiet. On planets, storms take on forms shaped by the presence of air, magnetism, and light. Gas giants, with their thick atmospheres and swirling bands, host tempests that can last centuries. Vast vortices spin with wind speeds beyond comprehension, driven by internal heat and sculpted by rotation. These storms carve patterns into clouds that glow under sunlight or reflect distant starlight in muted tones. Beneath their swirling tops, lightning erupts with brilliance that illuminates layers of atmosphere stacked like veils. A single bolt on a giant world can be thousands of times more powerful than those on Earth, igniting chemical reactions that alter the composition of the planet's skies. Moons with thin atmospheres feel storms differently. Charged particles from a parent planet's magnetosphere sweep across their surfaces in invisible floods. These storms carve subtle patterns into ice, change the chemistry of surface layers, and reshape the delicate balance of molecules drifting in their exospheres. Though silent and invisible to the eye, they leave behind traces that reveal how energy from a distant star can guide the evolution of even the smallest celestial bodies. In regions where young stars form, storms shape entire systems. Disks of gas and dust swirl around newborn suns, their particles colliding and sticking together in the earliest steps toward planets. Yet these disks are not still. Magnetic fields twist within them, driving streams of material toward the star or flinging it outward in towering jets. These jets, called outflows, stretch for light years, glowing softly in the dimness as they carve channels through the surrounding clouds. Each jet is a sign of a star still learning how to shine, releasing built-up energy through the narrow paths shaped by its magnetic field. On the surfaces of older stars, storms can grow more unpredictable. Red giants, swollen and unstable, shed their outer layers in slow, rhythmic pulses. These pulses send waves of gas drifting outward, carrying with them the raw materials for future worlds. Each pulse adds a thin shell of enriched matter to the space around the star, creating fragile bubbles that drift until the star's final collapse. Though not violent in the traditional sense, these gentle eruptions shape the chemistry of the galaxy, sending out carbon, oxygen, and other elements forged in the star's interior. Even white dwarfs, The cooling remnants of once bright suns can produce storms. When matter from a nearby companion star falls onto their surfaces, it accumulates until pressure and heat trigger sudden fusion. The result is a nova, a brilliant outburst that brightens the star for days or weeks. Though not destructive to the star itself, the eruption sends material hurtling into space at tremendous speeds, altering the environment of the entire system. Some white dwarfs repeat this cycle many times, each eruption like a heartbeat marking the star's slow cooling. Beyond stars and planets, storms occur on the grandest scales. Entire galaxies collide, stirring up tidal forces that send gas flowing into new orbits. Shockwaves spread through these galactic collisions, compressing clouds and triggering bursts of star formation. In the centers of merging galaxies, supermassive black holes can awaken, drawing in matter that heats into glowing disks and flares outward in jets that pierce the surrounding space. These jets carry energy across millions of light years, shaping the growth of clusters and carving cavities in the hot gas that surrounds them. Solar winds, the steady streams of charged particles flowing from stars, also contribute to storms across space. When these winds encounter magnetic fields around planets, they compress, ripple, and twist into beautiful auroras. But beyond the beauty, these interactions can strip atmospheres, alter climates, and transform worlds. A young star with a strong wind can erode the air of a small planet, leaving behind a barren surface where life may never take hold. In other systems, magnetic shields protect planets, allowing them to weather the storm and maintain conditions suitable for oceans and air. In the distant reaches of the universe, storms take on forms shaped by exotic matter. In accretion disks around black holes, gas spirals inward at immense speeds, heating into plasma that glows brighter than entire star clusters. Turbulence in these disks creates eruptions that flicker across seconds or years, revealing the chaotic dance of matter near the edge of the event horizon. These storms do not resemble anything found on planets or stars. They are governed by gravity so strong that time itself slows, giving the storms an eerie quality where motion and stillness coexist. Storms in space are not temporary outbursts. They are part of the universe's ongoing cycle of change. They reshape the structures around them, enrich the cosmos with new elements, and influence the evolution of planets and stars. In their light and shadow, we see the universe not as a static expanse, but as a place of constant motion, shaped by forces that erupt from the smallest particles to the largest cosmic structures. The universe appears, at first glance, to be built from light and gravity alone, a place where stars burn, planets drift, and darkness stretches between them in quiet simplicity. But beneath that simplicity lies a rich and intricate chemistry unfolding across unimaginable distances. Every glow in the sky carries the imprint of elements forged in ancient furnaces. Every cloud of drifting gas hides reactions too slow for human senses to detect. Even the faintest nebula, floating like a ribbon in the dark, is a laboratory where atoms form, break, combine, and reshape themselves into new possibilities. To peer into this chemistry is to uncover a hidden language written in colors, temperatures, and the delicate interplay of particles that drift as freely as dust in wind. Inside stars, chemistry becomes something deeper and more intense than any reaction found on a world like Earth. A star's core is a furnace where matter is squeezed and heated until atoms fuse with one another, releasing light that travels outward through layers of churning plasma. The process begins with hydrogen, the simplest of all atoms, merging into helium through a chain of collisions shaped by heat and pressure. As stars age, their cores grow hotter and their chemistry shifts, allowing new reactions to take place. Helium fuses into carbon. Carbon becomes oxygen. Elements grow heavier as the star's heart learns to carry more intricate patterns of fusion. This process is not chaotic. It is structured, almost like a cosmic recipe unfolding step by gentle step, guided by the laws that govern energy and matter. When stars swell into giants, their outer layers become places of slower, more delicate chemistry. Molecules begin to form as temperatures drop, drifting through the extended atmospheres in currents shaped by pulsations from within. These molecules absorb and emit light in unique patterns, leaving quiet fingerprints on the star's glow. Astronomers read these fingerprints from across the galaxy, deciphering the elements hidden inside. Even without touching a star, they can sense its chemical story, tracing its age, its past, and its future evolution. Nebulae, the great clouds that stretch across star-forming regions, offer a different kind of chemistry, slower yet more complex. Within them, gas drifts in waves, folding into shapes carved by gravity, radiation, and the shock waves of ancient explosions. Here, hydrogen molecules pair and break, carbon chains assemble, and dust grains gather layers of ice. The chemistry is fragile, influenced by faint glimmers of ultraviolet light and the passage of particles riding magnetic currents. Each molecule that forms becomes a seed for the next, building structures that grow more elaborate with time. Some of these molecules are so complex that they resemble the ingredients of life, scattered across cold expanses, light-years wide. In certain nebulae, intense radiation from young stars ionizes the surrounding gas, turning atoms into charged particles. These particles glow in vivid hues when electrons rejoin them, creating the familiar colors of emission nebulae. Red light from hydrogen, blue and green from oxygen, soft purples from helium. These colors are more than beauty. They are signals of chemistry in action, broadcasts from atoms, undergoing transitions that release energy into space. Every shift of an electron, every vibration of a molecule contributes to a pattern that astronomers can decode like notes in a distant melody. Interstellar clouds, especially the densest regions, host chemistry that unfolds in near silence. Temperatures there drop so low that reactions slow to a crawl, yet the cold allows fragile molecules to survive. Dust grains, coated in thin layers of ice, become platforms where atoms stick and meet. On these surfaces, hydrogen bonds to oxygen to form water. Carbon, oxygen, and nitrogen meet to create molecules that might drift for millions of years before they wander into a region warm enough to ignite new reactions. These icy grains travel through space like small archives, carrying with them a record of every atom that touched their surface. Sometimes clouds collapse under their own weight, and the chemistry changes again. As gravity tightens its hold, heat begins to build, breaking apart molecules and transforming dust into vapor. The cloud folds inward as the early stages of star formation begin. Yet before the new star is even born, the chemistry of its cradle shapes the environment around it. Some molecules break, others form for the first time under increasing heat. These early conditions determine the future ingredients available to the planets that may eventually orbit the newborn star. When massive stars end their lives in spectacular explosions, they contribute the richest chemistry of all. Supernovae scatter heavy elements into space, creating iron, gold, and many other elements that cannot be formed in smaller stars. These elements seed nebulae with material that enriches every future generation of stars and planets. Without these explosions, the universe would remain simple, lacking the complexity required for worlds, oceans, or life itself. The chemistry released in those final moments becomes the foundation for everything that follows. Even the seemingly empty regions between stars contain molecules drifting alone or in small clusters. Radio telescopes can detect their faint signals, revealing carbon monoxide, ammonia, formaldehyde, and even more intricate chains that would surprise anyone who imagines space as a sterile void. Some of these molecules survive for ages, protected by darkness and cold. Others are torn apart by radiation, only to reform again as fragments meet and combine in the quiet dark. The chemistry of the cosmos is patient. It unfolds across spans of time too long for human senses to follow directly. Yet every reaction, every fusion, every slow assembly of atoms contributes to the grand tapestry of the universe's evolution. Stars breathe out elements in winds, nebulae-shaped molecules in drifting pockets. Interstellar clouds cradle reactions in icy stillness, and as astronomers listen, they decode the hidden patterns in the light, uncovering the quiet chemistry that has been shaping the universe since its earliest ages. In this chemistry lies a reminder that the cosmos is not empty. It is always at work, building, unbuilding, and creating new forms from the simplest of ingredients. From the heart of a star to the cold depths of a drifting cloud, the universe weaves its elements through space with patience and grace, crafting everything that will one day shine, drift, collapse, or perhaps live. Far from the glow of any sun, beyond the warm drift of habitable worlds and the familiar order of orbits, wander objects that do not belong to any particular system. They move in silence through the deep, cold spaces between stars, guided only by gravity and chance. These cosmic travelers are ancient, solitary, and often invisible until they pass close enough to reflect a faint whisper of starlight. They carry stories written in their scars and their chemistry, stories shaped by violent expulsions, quiet drifts, and unimaginable spans of time spent in darkness. They remind us that the universe is full of wanderers, bodies that live their entire lives without the warmth of a parent star. Some travelers begin their existence as ordinary planets orbiting young suns. In the early chaos of a forming system, worlds collide, scatter, and ricochet through crowded orbits. A close approach with a giant planet can fling a smaller world outward at tremendous speeds, launching it into interstellar space. Once freed from its sun, the world cools rapidly. Its oceans, if it once had any, freeze into glaciers that thicken with time. Its atmosphere collapses into frost or escapes entirely. Yet the planet continues forward, following a lonely arc that may last longer than the lifespan of the star that cast it out. These rogue planets drift undetected, their surfaces silent, and their trajectories shaped only by the faint pull of distant gravity. Some of these worlds may still carry heat deep within. The decay of radioactive elements, or the slow release of energy from past compression, can keep their interiors warm even after billions of years in darkness. Beneath miles of ice, hidden oceans might churn slowly, warmed by internal tides or faint chemical reactions. If life ever emerged in such a world before it was thrown into the dark, it might continue in these protected depths, isolated yet persistent. These possibilities make rogue planets more than lost worlds. They are mysterious laboratories drifting between the stars. Other wanderers are smaller. Icy bodies the size of mountains or continents drift through space as interstellar comets. Their surfaces are layered with frozen gases and dust, preserved since the earliest epochs of their birth systems. When one of these visitors enters another star's domain, it awakens. Sunlight heats the ice, releasing plumes of vapor that create long, ghost-like tails stretching behind the nucleus. For a brief moment, the comet becomes visible, glowing as if startled from a deep cosmic sleep. Then it continues past the star and returns to the cold, leaving astronomers with only a fleeting glimpse of a traveler that may not pass this way again for another age. A few travelers are stranger still. Some fragments of rock and metal may come from ancient collisions between planets, ejected with enough force to escape their home system entirely. These shards drift through the galaxy as isolated messengers of distant worlds. If one were ever recovered and studied closely, its isotopes and minerals could reveal details about a solar system that formed far away under a different sun in another era entirely. Such fragments are rare, but their existence transforms the galaxy into a place where materials from one planetary cradle can, in theory, reach another. Asteroids can also wander between stars. Most remain bound to their suns, but occasionally a gravitational nudge sends one drifting outward at just the right speed. These rocky travelers carry the record of their formation in their layers, preserving chemical fingerprints that reflect the conditions in their ancient nurseries. Some may drift through space for millions of years before being captured by another star, adding their material to a new system. In this way, Even small wanderers contribute to the quiet exchange of matter that unfolds across the galaxy. Perhaps the most mysterious travelers are the interstellar objects that accelerate in unexpected ways. Their paths curve slightly as they pass through star systems, not quite matching predictions based solely on gravity. Some shed gas in faint, unsteady jets. Others show no clear signs of activity, yet still drift with subtle and unexplained motions. These anomalies spark questions about their structures, their compositions, and the forces acting upon them. Are they fragments of disrupted comets from other galaxies, or remnants of evaporated worlds shaped by extreme light? Their brief appearances leave scientists with puzzles that linger long after the object has faded from view. Drifting through the galaxy are also grains of dust, so small they would be invisible even if held in the hand. These grains were formed around dying stars or in the shock waves of supernova. They travel for eons, sometimes joining clouds that collapse into new suns, sometimes floating alone through the void. Each grain carries a memory of its origin, a chemical story etched in carbon, silicon, or ice. They move gently through space, nudged by radiation, guided by magnetic fields, and drifting without destination until chance brings them into a region where they can contribute to the birth of new worlds. There are travelers that are neither planets nor rocks, but drifting clouds of gas that have broken away from larger structures. These clouds move slowly, shaped by the faint gravity of distant stars and the residual currents of ancient explosions. Their edges blur with time, scattering atoms across thousands of miles. Sometimes they pass through the outskirts of a system, altering the chemistry of its outer worlds. Other times they drift unnoticed, dissolving gradually into the wider interstellar medium. Some of the oldest travelers are stellar remnants that escaped their former homes through violent events. A supernova can fling a neutron star outward at immense speeds, sending it hurtling through the galaxy like a stone thrown from a sling. These runaway neutron stars spin as they drift, emitting pulses of radio waves that sweep across space. Their paths cross through regions where stars have yet to form, through the borders of spiral arms and into the dark halo far above the galactic plane. Though tiny compared to stars, they carry extraordinary density and magnetic fields, altering the space they pass through in subtle but lasting ways. All of these travelers move within a galaxy whose gravity binds them loosely, but not intimately. Their journeys may last billions of years. They may spend their entire existence without passing close to a star, without warming under any light, without touching another world. Yet, they continue onward. They remind us that the universe is not built solely from systems with suns at their centers. It is also shaped by the wanderers who navigate the darkness between them. Silent couriers of history, moving through cold and endless night. In the calm arrangement of stars scattered across the night sky, it is easy to imagine the universe as a place of predictable paths, where every star and planet follows a neat orbit and every system behaves with quiet order. But the truth is far more intricate. The cosmos is full of strange orbits, tilted paths, and wandering bodies that move with rhythms shaped by ancient encounters. These patterns influence entire neighborhoods of stars, bending their histories into shapes that only become clear when you look across great swaths of time. Nothing in space remains in perfect symmetry for long. Instead, every orbit holds traces of past collisions, close approaches, or gravitational nudges that ripple outward, affecting the motion of countless objects around them. Some of the most intriguing orbits are those of stars themselves. In many regions of a galaxy, stars move with regularity, circling the galactic center in smooth arcs. Yet scattered throughout are stars whose paths tilt high above the plane or dive downward through the disk in long, sweeping motions. These stars do not follow the usual rotation of their stellar neighbors. They originate from ancient mergers, remnants of dwarf galaxies consumed long ago, still carrying the momentum of their former homes. Their unusual orbits carve three-dimensional loops through the galaxy, crossing paths with more settled stars and subtly influencing their motion through cumulative gravitational whispers. Planetary systems also reflect the complexity of cosmic dynamics. Some stars host planets that orbit in tight, orderly circles, while others harbor worlds that move along wildly elongated paths. These eccentric orbits can stretch so far from the star that seasons span centuries and temperatures swing between extremes. Such orbits often hint at chaotic beginnings. A passing star long ago may have skimmed the edge of the system, tugging planets into new trajectories, or a giant planet may have migrated inward, scattering smaller worlds into elongated loops. These patterns tell a story of youth, competition, and the delicate dance of gravitational forces. In certain systems, planets orbit not in the equatorial plane of the star but at steep angles, sometimes nearly perpendicular to the star's rotation. This misalignment defies early expectations that planets should form neatly from the flattened disk of gas around a newborn star. But the universe rarely obeys neatness. A close encounter with another star, or the influence of a massive companion planet, can torque the entire system, tilting the orbital plane, or even flipping it. These misaligned worlds move through their year as if tracing paths across invisible scars left by ancient disruptions. Binary star systems add further complexity. When two stars orbit each other, their combined gravity shapes the movements of any surrounding planets. Some systems host planets that orbit just one of the stars, weaving delicate paths that remain stable only because they avoid the shifting pull of the companion. Other planets orbit both stars together in wide loops, rising and dipping as the stars dance around their shared center of mass. In more chaotic systems, gravitational resonances build, stirring orbits into unpredictable shifts. Planets may be pushed outward, trapped in rhythmic exchanges of momentum, or flung entirely from the system. Every binary system is a story of shared motion, tension, and balance. Strange orbits also shape the clusters where stars are born. In dense clusters, stars pass close to one another, their gravity tugging at each other's disks and planets. These close encounters can distort orbits or strip planets away entirely, sending them drifting into interstellar space. Over time, the cluster thins as stars drift apart, but the scars of those early interactions remain. Some stars emerge with planets in stable, circular orbits. Others carry planets that loop widely or tilt at unexpected angles, traces of the crowded environment they once inhabited. Beyond individual systems, entire regions of a galaxy move in patterns that reflect both local and large-scale forces. Spiral arms, though visualized as static structures, are actually patterns formed by density waves. Stars drift in and out of these regions, their motions subtly altered by the gravitational compression within the arms. As stars pass through, their orbits shift slightly, like travelers moving through a slow-moving crowd. These shifts ripple outward, influencing nearby systems and shaping the overall flow of stellar neighborhoods. In the galactic halo, far above and below the disk, star streams stretch across the sky like faint glowing rivers. These streams were once dwarf galaxies or clusters captured by the Milky Way's gravity. As they were pulled apart, their stars settled into elongated orbits that continue to guide their motion long after the original structure dissolved. Each stream moves as a collective memory of its past, influencing the halo and occasionally crossing the paths of stars from the disk. Their presence reveals the galaxy's history of mergers and encounters, written not in light but in motion. Some orbits reveal hidden companions. When a star wobbles gently instead of moving smoothly through space, the wobble can indicate the presence of an unseen object tugging on it. These invisible companions might be planets, brown dwarfs, or even black holes. Their gravitational influence shapes the star's motion, creating patterns that astronomers read like coded messages. The orbit of the star becomes a map of the forces acting upon it, a subtle dance of unseen partners moving in silence. There are also objects whose orbits defy long-term stability. These wanderers, moving on paths nearly parabolic or hyperbolic, drift into star systems only briefly before being flung back into interstellar space. Their presence can disturb the orbits of planets, moons, or asteroids, leaving behind altered trajectories that persist long after the visitor has vanished into the void. Such encounters remind us that orbital patterns are never fully closed systems. The universe is too vast, too dynamic, too full of motion for complete isolation. Over millions of years, even small gravitational tugs accumulate. A passing gas cloud, a nearby supernova, or the slow drift of stars through spiral arms can reshape orbits subtly and progressively. These influences ripple through stellar neighborhoods, altering the paths of stars and planets in ways that only become visible across enormous spans of time. No orbit remains perfectly constant. Everything drifts, adjusts, and responds to the vast interconnected forces surrounding it. In the end, strange orbits and unexpected patterns reveal a universe where motion is history. Every tilted path, elongated loop, or chaotic twist tells a story of past encounters, ancient disruptions, or the quiet pull of distant gravity. Stellar neighborhoods are shaped not by stillness, but by the memory of movement, written in the arcs traced by stars and planets across the deep fabric of space. Across the vastness of space, where silence stretches farther than any horizon and darkness hangs with immeasurable depth, the universe still keeps time. It does so not with ticking hands or gears, but with signals, pulses, and repeating rhythms that sweep across the cosmos like the breath of something ancient. These rhythms are steady, patient, and enduring, revealing order hidden within the apparent chaos. To listen to them is to hear the universe recount its cycles, each beat shaped by forces older than stars themselves. Some of the most reliable cosmic clocks are pulsars, the rapidly spinning remnants of stars that ended their lives in brilliant explosions. When these massive stars collapse, their cores compress into neutron stars that rotate with astonishing speed, sometimes hundreds of times each second. Beams of radiation, born near their magnetic poles, sweep across the sky with perfect regularity. Each rotation produces a flash that can be detected from across the galaxy, arriving with such precision that even the most advanced human-built clocks seem almost clumsy by comparison. These pulses travel through space unhindered, crossing light years with their rhythm intact. When astronomers record them, they are capturing the heartbeat of a dead star that continues to mark time long after its surface has gone dark. Not all pulsars spin uniformly. Some slow as they age, their rotations stretched by the gradual loss of energy. Others glitch, jumping abruptly into faster cycles when tension inside their dense interiors suddenly shifts. These changes offer rare glimpses into the strange physics at work within matter packed beyond earthly comprehension. The star's interior behaves partly like a solid and partly like a superfluid, and its pulses reflect these hidden structures. Even in their irregularities, neutron stars reveal cosmic patterns that unfold over spans far greater than human lifetimes. Beyond pulsars, there are stars whose brightness varies with a quiet, predictable rhythm. Cepheid variables expand and contract in cycles shaped by the delicate balance between gravity and pressure. Their light grows brighter as their outer layers stretch outward and dims as they fall back inward. These cycles repeat with such reliability that astronomers use them as standard candles to measure vast distances. The time between peaks in their brightness acts like a clock whose hands span days or months instead of seconds. Observing their pattern is like watching the slow breathing of a star, each pulse carrying the weight of its inner physics. Other variable stars display more complex rhythms. Some experience eruptions driven by magnetic cycles, flaring in energy and then settling again. Others shift in brightness due to the presence of orbiting companions, their light dimming when one star passes in front of the other. These regular eclipses create repeating shadows that act like cosmic metronomes, reminding us that even in distant systems, orbits and cycles maintain their quiet order. Rhythms extend beyond individual stars. Entire galaxies carry patterns of motion that unfold over millions of years. As they rotate, their spiral arms move like slow-moving waves, guiding stars into curved paths. While these motions are far too gradual for direct human observation, Their consistency shapes the evolution of stellar neighborhoods. Over time, the galaxy's rotation influences when stars form, how clusters drift, and how matter settles into long arcs of starlight. Though invisible in a single lifetime, this rotation is one of the largest and most enduring clocks in existence, marking epochs rather than moments. Even black holes participate in cosmic timekeeping. Around some of them, hot gas spirals inward in disks that flicker with rhythmic variations in brightness. These flickers, shaped by turbulence and orbital motion near the event horizon, create quasi-periodic oscillations that echo through the high-energy light they emit. Each oscillation reveals how matter behaves as it approaches the point of no return, tracing patterns that reflect the curvature of space-time itself. The rhythm is chaotic yet meaningful, like a pattern woven from the edge of the unknowable. In regions where stars form, pulsating jets of material burst from young suns in periodic intervals. These jets carve paths through surrounding gas, creating knots and ridges that mark each surge of energy. The intervals between these bursts reveal cycles unfolding within the forming star, shaped by magnetic forces and accretion patterns. Over time, these rhythms help shape the environment where future planets may emerge, imprinting a memory of the star's youth into the structure of its surroundings. There are even signals that stretch across galaxies, produced by phenomena so powerful that their echoes travel uninterrupted through space. Fast radio bursts explode with brightness for only a moment, yet some repeat in cycles that astronomers still struggle to decode. Their rhythms are irregular but intentional, hinting at extreme environments where magnetic fields twist particles into sudden pulses. Each burst is a fraction of a second long, but the intervals between them hold clues about the processes driving their creation. Cosmic rays, though seemingly chaotic, also arrive in patterns. Their intensity ebbs and flows with the solar cycle, following the 11-year rhythm of the sun's magnetic field. This rhythm shapes the amount of radiation that drifts into the inner solar system, creating cycles that influence planetary atmospheres and even the chemistry of certain molecules. Though subtle, these patterns reveal the sun's influence extending far beyond its visible surface. Even the expansion of the universe has a rhythm, though stretched across unimaginable distances. The cosmic microwave background carries tiny fluctuations, relics of oscillations that occurred when the universe was young and dense. These primordial sound waves, frozen into the pattern of the background radiation, preserve the earliest rhythms of matter itself. They are the oldest known cosmic clocks, marking a time when the universe shifted from fire into structure. All these signals, pulses, and cycles weave together into a grander sense of cosmic time. They show that the universe is not static, but filled with recurring motions that echo through space like quiet drum beats. Some tick with the swiftness of a rapidly spinning star. Others stretch across ages, marking changes that only reveal themselves when viewed over eons. Together, they create a network of natural clocks that help us understand not just where objects are, but how they change, how they age, and how the cosmos itself has evolved. In listening to these rhythms, we hear not only the soundless heartbeat of the universe, but also the passage of time on scales far beyond our own. Each pulse is a reminder that everything, from the smallest particle to the largest galaxy, moves in patterns shaped by the deep architecture of reality. To imagine space as empty is to overlook the restless ocean that fills it. Even in the darkest stretches between stars, particles drift, radiation pulses, and invisible currents shape the motion of everything that exists. Space behaves less like a void and more like a vast sea, its waters made not of liquid but of charged particles, photons, magnetic fields, and the ceaseless flow of energy. Every object that moves through this ocean leaves a wake, and every wave that travels through it carries the memory of distant events. The silence may fool the senses, but beneath that silence lies constant activity, subtle and persistent. The most familiar currents are those of charged particles streaming outward from stars. A star's surface may appear tranquil from afar, but it releases a continuous wind of electrons and protons that travel outward in all directions. This stellar wind grows thinner with distance, yet never truly disappears. It fills the surrounding region, forming a bubble shaped by the balance between the star's outward breath and the incoming pressures of the galactic environment. In our own solar system, this bubble extends far beyond the last planets, a vast protective envelope that shields the inner worlds from higher energy radiation. Yet even within this envelope, the solar wind flows in shifting patterns shaped by magnetic storms and quiet cycles. It streams outward in spiraling paths, carried along by the sun's rotation, creating waves that sweep past planets with gentle but continuous force. Beyond the influence of any single star, radiation permeates the galaxy. Some of it is soft and diffuse, the leftover glow from the universe's first light. Some arrives in sudden bursts from distant catastrophes. Photons of every wavelength move through space like ripples on a vast pond, carrying information from the regions where they originated. They bounce off dust grains, scatter through clouds, and lose energy as they drift across expanding space. In certain wavelengths, they illuminate structures that would otherwise remain hidden, revealing filaments of gas and pockets where stars are waiting to form. Radiation becomes both messenger and sculptor, influencing temperatures, chemistry, and the evolution of entire regions. Cosmic rays add another layer to this ocean. These high-energy particles travel at speeds close to that of light, born from the shock waves of exploding stars or the acceleration near black holes. They wander through space in tangled paths, guided by magnetic fields that twist and bend like underwater currents. When these rays reach planets, they interact with atmospheres, creating cascades of secondary particles that rain downward. Though silent and invisible to the eye, cosmic rays alter the chemistry of planets, trigger reactions in clouds, and leave faint imprints on the surfaces they strike. They remind us that even the emptiest regions are filled with particles carrying immense energy. Magnetic fields weave through this ocean as well, stretching across light years. They guide particles into spirals, redirect flows of gas, and influence the motion of charged dust. In galaxies, magnetic lines trace patterns that mirror the shape of spiral arms, giving structure to regions where stars form. Around planets, magnetic fields create magnetospheres that deflect solar wind, carving bow shocks and long streaming tails in the surrounding plasma. These shapes resemble the wakes of ships moving through deep water, formed by the interaction between a planet's magnetic presence and the flowing sea of particles around it. Even the motion of planets and stars reveals the nature of this cosmic ocean. As objects move, they create disturbances that travel outward in waves. In dense regions, such as the centers of galaxies or star-forming clouds, these motions cause turbulence that influences how matter gathers. Gas clouds swirl, collapse, and break apart in eddies shaped by gravity, magnetic fields, and particle flow. These eddies can determine which pockets become new stars and which dissolve back into the surrounding medium. Over millions of years, these motions sculpt entire stellar nurseries, turning drifting gas into intricate webs of creation and destruction. In the colder regions between stars, particles move at slow speeds, yet they still drift in patterns governed by faint fields and distant influences. These particles form the raw ingredients for new worlds, floating through space until a gravitational pull gathers them into larger structures. Dust grains collide gently, sticking together through electrostatic forces, forming the earliest seeds of planets. Even in this gentle drift, motion persists. Every particle responds to the faint currents of radiation pressure, the magnetic threads that stretch across the galaxy, and the gravity of passing stars. On the largest scales, galaxies themselves swim through a medium filled, not with gas, but with dark matter, a mysterious substance that creates the gravitational landscape of the universe. Though dark matter cannot be touched or seen, its presence shapes the paths of galaxies as they move through cosmic space. It forms massive halos around each galaxy, altering motion in ways that resemble the resistance and flow of a deep, unseen sea. Entire clusters of galaxies drift together within this medium, their interactions creating waves that ripple through the surrounding dark matter, influencing the paths of others far away. Even the expanding universe contributes to this ocean. Space itself stretches, altering the motion of particles and the energy of radiation. Photons lose energy as they travel, their wavelengths lengthening like waves dispersing across a broadening surface. The movement of galaxies becomes not only a response to gravity but also a consequence of space itself growing. This expansion adds yet another layer to the motions that fill the cosmos, a slow but persistent drift that carries distant worlds farther apart with every passing moment. Through all these layers, the universe behaves not as an empty stage but as a fluid environment filled with motion, currents, and interactions. Particles sweep past stars and winds. Radiation flows through nebulae. Magnetic fields bend and twist. Dust drifts in slow spirals. Galaxies glide through halos shaped by forces we cannot see. Every movement, no matter how small or subtle, contributes to the evolving shape of the cosmos. To understand space in this way is to recognize that nothing within it is ever truly still. The quiet between stars is filled with motion. The darkness between galaxies carries energy. Even the coldest regions hum with the faint drift of particles older than planets. Space is an ocean without edges, its currents extending across the universe, shaping everything they touch. The universe presents itself with a calm, indifferent face, stars scattered across a dark canvas like a simple decoration. Yet behind that calm lies a vastness so profound that human intuition folds under its weight. The scales at play stretch beyond familiar experience, into realms where distance becomes almost abstract and time unspools in threads too long for the mind to follow. To contemplate these scales is to stand at the edge of comprehension, reaching towards something that feels both real and unreal at once. Space is not simply large. It is layered with magnitudes that reshape the very sense of what it means for something to be far, or old, or immense. Consider a beam of starlight traveling across billions of miles before it reaches Earth. To the photon, its journey is unbroken. It simply moves forward, indifferent to the years passing around it. But for us, the scale transforms that light into a story about time itself. A star seen tonight might have shifted or even vanished in the intervening years. Yet its last message continues toward us, arriving long after the moment it was released. Each point of light becomes a postcard from the past, a reminder that the universe stretches not only across distance but across history. It teaches us that to see the sky is to look backward, each glance a meeting between now and then. Yet even light struggles to bridge certain expanses. Galaxies lie separated by distances so vast that the mind resists giving them shape. These are stretches where the usual language of miles or kilometers loses meaning, replaced by light years that measure the time it takes for illumination to cross the void. Some galaxies are so distant that their light began traveling before our sun existed, before Earth was more than dust drifting in a disk around a forming star. When that light enters a telescope, it does more than reveal shape or color. It reveals a version of the universe that no longer exists, captured in the act of becoming. Within galaxies, distance stretches in other ways. Stars may seem crowded in an image, their points of light so close they appear almost to touch. But in reality, they lie separated by expanses so wide that an entire solar system could drift between them unnoticed. The emptiness between stars is immense, a gulf where planets, comets, and dust drift without encountering another world for centuries. Even within our own neighborhood, the nearest star lies so far away that if the sun were scaled down to the size of a small glowing bead, that neighboring star would be another bead placed hundreds of miles away. Such scales force the imagination to stretch, to accept that what appears clustered from a distance is in truth scattered across unimaginable spaces. Then there are structures that span even greater realms. Galaxy clusters form vast congregations held together by gravity, stretching across millions of light years. Within them, galaxies drift like islands in an ocean, following slow currents shaped by dark matter. Larger still are superclusters, chains and webs of galaxies stretching into filaments that crisscross the cosmos. These filaments weave a structure so vast that even diagrams fail to capture their length. If a single galaxy were scaled to the size of a grain of sand, a filament might stretch farther than the width of a continent. The vastness becomes almost poetic, a quiet testament to the scale on which the universe builds its architecture. Yet even these immense structures are small compared to the distances between them. Voids stretch between filaments, regions so empty that they contain fewer atoms than a breath of air. These voids are not simple gaps. They are deserts carved by cosmic expansion, places where matter drifted outward over billions of years, leaving behind a silence deeper than any known on Earth. The scale of these voids further challenges intuition, for they can span hundreds of millions of light years, vast bubbles of near-nothingness hanging between the threads of the cosmic web. Not all scale in the universe concerns distance alone. Some phenomena stretch the understanding of time. Stars live for spans that dwarf human history. Some burn brightly for only a few million years, collapsing after a brief but spectacular existence. Others burn slowly, steadily, for tens of billions of years, outlasting entire eras of cosmic change. There are stars in the sky older than the galaxies they now drift within, their lifespans stretching beyond the rise and fall of structures around them. Their endurance adds another layer to the cosmic scale, one measured in epochs rather than centuries. When galaxies collide, the encounter unfolds over spans so long that a human lifetime registers as less than a blink. Two galaxies may pass through one another over hundreds of millions of years, their stars rarely colliding despite the dense appearance from afar. Gravity pulls and shapes their forms, stretching arms, igniting bursts of star formation, and eventually merging them into a new, larger structure. To watch such a collision in real time would require patience no creature could possess. Yet telescopes capture snapshots from different stages across the universe, allowing astronomers to piece together the story of these vast dances through the evidence scattered across millions of light years. Even the expansion of the universe challenges comprehension. Space itself stretches, carrying galaxies with it like leaves drifting on an invisible current. The rate of this expansion accelerates across billions of years, altering the distances between galaxies in ways that defy everyday experience. One day, distant galaxies may recede so quickly that their light can no longer reach us. The visible universe will shrink in content even as space continues to grow, leaving behind only the galaxies gravitationally bound to one another. Scale here becomes dynamic, a changing measurement shaped by forces no one can see directly. At the smallest end of the spectrum, scale stretches again. Particles too tiny to observe directly influence the behavior of stars, nebulae, and galaxies. Quantum fluctuations ripple across the vacuum, shaping the earliest seeds of cosmic structure. These fluctuations, smaller than an atom, were stretched by the rapid expansion of the early universe into patterns that now form the framework of galaxy clusters. In this way, the universe connects the microscopic with the grandest scales imaginable, linking the behavior of particles smaller than dust to structures larger than imagination. The cosmos is full of phenomena that require the mind to stretch, to abandon familiar comfort, and embrace the sheer magnitude of creation. Distance becomes time. Time becomes structure. Structure becomes a story written across expanses so great they can only be grasped through metaphor. And yet, in contemplating these scales, we find a strange clarity. The immensity of the universe does not diminish existence. It deepens it, inviting us to look beyond what we know and reach into realms where the vast and the intimate meet in quiet harmony. Galaxies may appear serene when seen from afar, their spiral arms unfurling like gentle currents of light, their halos glowing softly against the dark. But beneath that calm lies a lifetime of change, shaped by collisions, growth spurts, quiet aging, and cycles of creation and loss. A galaxy is not a static island of stars. It is a living structure, evolving over billions of years through processes that often defy expectation. To understand how galaxies grow and age is to witness the slow, intricate choreography that shapes the grand architecture of the universe. They begin as small gatherings of gas and dark matter, clouds collapsing under gravity's steady pull. These early galaxies were nothing like the majestic spirals we see today. They were turbulent, irregular, and filled with massive young stars that burned fiercely and died quickly. Supernova explosions seeded their surroundings with heavier elements, stirring the gas and shaping the early chemistry of the galaxy. Over time, these small, chaotic systems merged with one another, each collision reshaping their structure. Such mergers were not catastrophic crashes but slow interweavings, where stars passed through one another unharmed while gas clouds collided and ignited waves of new star formation. Through such encounters, galaxies grew from small fragments into ever larger systems. As galaxies matured, they began to settle into recognizable forms. Some became spirals, with rotating disks that organized gas and stars into sweeping arms. These arms are not solid structures but patterns created by density waves, regions where material temporarily slows and concentrates before moving onward. Within these waves, gas clouds compress and form new stars, giving spiral arms their bright, beaded appearance. It is within these glowing bands that many of the universe's most dynamic processes occur, each newborn star contributing its warmth and radiation to the surrounding medium. Other galaxies evolved into elliptical shapes, massive and smooth, lacking the intricate patterns of spirals. These giants often formed from mergers between spirals, their graceful rotation disrupted by the gravitational chaos of collision. Without the orderly motion required to maintain a disk, their stars settled into more random orbits, creating the round or elongated shapes we observe. Ellipticals often contain older stars, their gas supplies long consumed or expelled, leaving behind a population of suns that age quietly, with little new formation to replenish them. They are the elderly giants of the cosmos, rich in history, but calm in their later years. Yet galaxies do not age uniformly. Some enter periods of intense growth known as starbursts, where star formation explodes in sudden abundance. These bursts can be triggered by collisions, close encounters, or the inflow of new gas from intergalactic space. During a starburst, a galaxy may form stars at rates hundreds of times greater than usual, lighting up with clusters of bright, short-lived giants. The energy released during these episodes can be so immense that it drives winds outward from the galaxy, pushing gas into halos and beyond. When the burst ends, the galaxy may be left depleted, entering a quieter stage of evolution as it waits for new material to return or drift inward. At the centers of many galaxies lie supermassive black holes, silent engines that influence growth in surprising ways. When gas spirals toward these black holes, it forms a glowing disk of material, releasing enormous energy as it falls inward. Some galaxies host active centers where jets of plasma erupt outward, extending for thousands of light years. These jets heat surrounding gas, preventing it from cooling and forming new stars. In this way, a galaxy's central black hole can regulate its growth, acting as a kind of cosmic thermostat. When the black hole is quiet, star formation may flourish. When it awakens, the galaxy slows its growth, entering a phase of rest. Galaxies also grow by feeding on their surroundings. Streams of cold gas flow along cosmic filaments, funneled by gravity into the waiting arms of galaxies. This gas becomes the raw material for new stars, sustaining the galaxy's vitality. In some regions, small satellite galaxies drift too close, drawn inward until they are slowly stripped apart. Their stars merge with the larger galaxy, enriching its halo with ancient, wandering suns. These processes extend across billions of years, each interaction adding subtle layers to the galaxy's structure. As galaxies age, their colors shift. Young galaxies glow blue with the light of massive, hot stars. As these stars die and fewer new ones form, galaxies take on warmer, redder tones, dominated by older stars that shine steadily but less intensely. This gradual reddening marks a galaxy's transition into maturity, a sign that its most active period of star formation has passed. Over time, stellar populations age together, their orbits shifting slightly as gravitational interactions redistribute energy across the galaxy. The outskirts of galaxies tell their own stories. Faint streams of stars loop outward in trails that record past interactions. These tidal tails are remnants of collisions, like faint scars stretching across the darkness. Some tails eventually blend back into the galaxy, while others remain as delicate archways connecting to smaller companions. In these subtle structures, astronomers read the history of encounters, long forgotten, events that shape the galaxy's path through time. Even as galaxies continue to evolve, the universe around them changes as well. The expansion of space gradually increases the distances between galaxies, slowing the pace of collisions. Some galaxies, once part of bustling clusters, will drift into quieter isolation as cosmic expansion continues. Others will merge into ever larger structures, ultimately forming massive elliptical galaxies with little new star formation. In the far future, only the most gravitationally bound collections of galaxies will remain close enough to interact. Through all these stages, galaxies remain dynamic, never fixed in their appearance or behavior. They grow through mergers and gas inflows. They age through star formation and depletion. They evolve through subtle shifts in motion, structure, and color. Every spiral, every elliptical, every irregular shape represents a long, complex journey from primordial gas to structured brilliance. In watching galaxies across the universe, we witness not just distant light, but entire lifetimes unfolding on scales that dwarf imagination. Their growth, their aging, their constant reshaping reveal a cosmos that is always in motion, always transforming, always writing new chapters in the story of creation. Before a star ever flares into brilliance, before a planet ever solidifies beneath a newborn sun, there are places in the cosmos where beginnings gather quietly in the dark. These are not regions of warmth or radiance. They are shadowed realms, cold and dense, where hydrogen drifts in thick clouds and dust settles into veils that hide everything behind them. To human eyes, these places appear as empty patches of sky, dark spaces where starlight seems to vanish. But within them, gravity is at work, sculpting the raw material of future suns and their orbiting worlds. In these cold cradles, the universe rehearses creation over and over, always in silence. A stellar nursery begins as a cloud larger than any star it will ever produce. It stretches for light years, a drifting accumulation of atoms cooled almost to the point of stillness. Tiny particles of dust shelter fragile molecules, allowing them to survive radiation from distant stars. As the cloud thickens, small eddies form where turbulence gathers matter into knots. Each knot is a seed, a region just dense enough for gravity to tighten its grip. It is here that the earliest hints of a star take shape, long before it emits even the faintest glow. These knots collapse slowly at first, folding inward like fabric caught in a gentle downward pull. As the collapse continues, pressure rises deep inside, and the core begins to warm. The first stages are hidden. Not even the most powerful telescopes in visible light can pierce the dark dust that wraps these forming stars. But infrared instruments reveal hints of their presence, soft glimmers tucked within thick clouds. These rising temperatures mark the transition from a simple clump of gas to a protostar, a growing sphere of material whose future is already determined by its mass. A small protostar will one day shine gently as a red dwarf, burning steadily for trillions of years. A massive one will blaze with fierce intensity, living fast and dying in spectacular explosions. For now, though, each newborn star waits in obscurity, surrounded by swirling debris As the collapsing cloud spins faster, a disk forms around the growing star. This disk is the birthplace of planets. Dust grains collide, stick together, and drift inward, gathering into pebbles, then rocks, then enormous bodies that carve paths through the gas. Over time, these bodies grow into planets, moons, and asteroids. It is a slow accumulation, shaped by gravity, collisions, and the ever-changing motion within the disk. Some worlds form close to the star, too hot for water or ice, while others take shape far away in colder regions where frozen compounds drift like tiny comets waiting to be assembled. Planetary systems are not designed. They are sculpted through messy, dynamic interactions that unfold for millions of years. Beyond these disks, larger structures begin to influence the formation of stars and planets. Radiation from nearby massive stars carves away at the clouds, creating glowing edges where gas evaporates into space. These brilliant rims mark boundaries between regions of collapse and regions of dispersal. Some areas are compressed by shock waves from supernova remnants, triggering new rounds of star formation. In other places, intense ultraviolet light strips away fragile molecules, halting the birth of stars entirely. A stellar nursery is both a cradle and a battlefield, shaped by forces that create and destroy with equal ease. Once fusion ignites at the core of a protostar, it becomes a true star, shining for the first time. The surrounding gas begins to clear, pushed outward by stellar winds and radiation. What was once invisible emerges slowly, revealing clusters of young stars glowing blue and white against the dispersing dust. These clusters contain siblings born from the same vast cloud, but they will not remain together. Over millions of years, their mutual gravitational ties will weaken, and the cluster will dissolve. The stars will drift apart, each beginning its solitary journey around the galaxy. Even our sun was once part of such a cluster, its siblings now scattered far away, indistinguishable among the countless stars. In some clouds, the density becomes so great that entire chains of stars form in elongated filaments. These filaments stretch like luminous threads across dark space, each knot a future star waiting to ignite. Observations of these structures reveal that star formation is not random, but shaped by the underlying architecture of the cloud. Magnetic fields guide the collapse, channeling gas along narrow paths. Turbulent flows carve pockets and channels, influencing where stars will emerge. Within these filaments, the balance of pressure, gravity, and magnetism creates a delicate environment where the smallest disturbances can decide the fate of whole generations of stars. Planets born from these regions inherit the history of their formation. Their composition reflects the chemistry of the cloud, the radiation they endured, and the collisions that sculpted their surfaces. Some worlds may form with thick atmospheres rich in volatile compounds. Others may be dry and rocky, shaped by early heat and close proximity to their star. Comets and asteroids become messengers, carrying water and organic material across developing planetary systems. These small, icy bodies are remnants of the early disk, untouched by fusion, preserving the original chemistry from which life might someday emerge. Not all stars succeed in growing large enough to ignite fusion. Some collapse only partially, forming brown dwarfs, objects too small to sustain steady nuclear reactions. These dim, cool bodies drift at the edges of star-forming regions, faint reminders of the narrow line between starlight and silence. They may host planets of their own, warmed only by internal heat, quiet worlds orbiting a star that never fully awakened. The environment that fosters star formation is only temporary. Eventually, the cloud disperses. Radiation from young, massive stars tears holes in the gas, creating cavities and chimneys that open into the surrounding medium. Winds sweep away dust and thin the remaining material until the nursery is no longer able to form new stars. What remains is a cluster of young suns lighting the emptiness where the cloud once was. Over time, the memory of the cloud fades, leaving only the stars to tell the story of their shared origin. To watch a star-forming region is to witness the universe breathing. It is a reminder that creation unfolds in silence, in darkness, long before light emerges. These hidden environments cradle the beginnings not only of stars but of planets, moons, and the conditions that may one day support life. Every star in the sky was once a quiet knot in a cloud, waiting to ignite. Every world began as a grain of dust, drifting in a disk around a newborn sun. And so the cosmos continues its patient cycle of beginnings, shaping the next generation of stars in shadows where no starlight yet shines. In the universe, endings and beginnings are often the same event viewed from two different distances. A star's collapse, a planet's shattering, a galaxy's quiet unraveling may look like devastation. Yet, in their aftermath, the cosmos arranges itself into new forms, richer and more varied than before. If there is a single truth written into the workings of the universe, it is that creation rarely arrives without upheaval. Destruction is not the conclusion of a story, but the spark that lights the next one. Consider the life of a massive star. For millions of years it burns fiercely, fusing hydrogen, then heavier elements as it ages. At its peak, it shines with a brilliance that can outshine entire galaxies, its light traveling across space long after the star itself is gone. Deep within its core, however, the last stages of fusion build toward catastrophe. Iron accumulates in a core that cannot burn any further, and gravity, patient until now, tightens its grip. In a moment so fast that it defies ordinary comprehension, the core collapses and rebounds, sending a shockwave outward that tears the star apart. The explosion is a supernova, a burst of light so powerful that it can briefly illuminate distant worlds. To the star, this is the end. But to the universe, it is a beginning. The explosion scatters heavy elements, those precious ingredients forged in the star's furnace, into the surrounding medium. Calcium, oxygen, iron, carbon, gold, and countless other atoms drift outward, seeding the galaxy with material from which new stars and planets will form. Entire solar systems owe their existence to the death of a massive star. Every atom in your bones, every breath you take, is the legacy of a star that destroyed itself so creation could continue. Some supernova leave behind compact remnants, neutron stars or black holes, objects so dense and extreme that they defy ordinary behavior. Neutron stars spin rapidly, sending beams of radiation across space like cosmic lighthouses. Black holes, with their immense gravity, reshape the regions around them. Yet even these remnants play a role in creation. When neutron stars collide, they produce some of the heaviest elements in the universe. In the short blink of a kilonova explosion, gold and platinum spill into space, forming clouds of material that may one day join new worlds. What seems like annihilation becomes a forge, shaping treasures from the wreckage. Destruction also unfolds on quieter scales, shaping planets and moons through constant bombardment. In the early days of a solar system, collisions are the rule rather than the exception. Planets grow by gathering smaller bodies, but these gatherings are violent. Each impact melts rock, vaporizes dust, and reshapes entire worlds. Earth itself was struck by a body roughly the size of Mars early in its history. The collision ripped away vast amounts of material that formed a glowing ring around the young planet. From that ring, the moon gradually took shape. Today, the moon stabilizes Earth's tilt, shapes the tides, and illuminates the night. But its existence is the direct result of a moment that nearly destroyed our planet. Even now, impacts continue across the solar system. Craters on the moon and Mars are reminders of events that reshaped their surfaces, altering climate, geology, and potential habitability. Asteroid strikes on Earth have reset the planet's biological timeline more than once, sweeping away dominant species and clearing the way for new ones. The dinosaurs' extinction, devastating as it was, opened ecological space that allowed mammals to flourish. In the cosmic balance, destruction created the world as we know it. On grander scales, galaxies collide and merge, tearing apart their structures while giving rise to new ones. When two galaxies approach each other, their shapes distort, stretching into long tidal tails. gas clouds crash together, triggering intense waves of star formation that ignite new generations of stars. Over billions of years, the galaxies blend into a single larger system. These mergers are slow, elegant, and transformative. The Milky Way itself is built from dozens of such encounters, each one adding stars, reshaping the disk, and enriching the halo. Future generations will witness an even grander merger when the Milky Way and Andromeda draw together, their stars passing untouched, even as their gravitational dances reshape both galaxies. The final result will be a completely new form, a galaxy born from the dissolution of two others. Destruction also plays out in smaller, stranger moments, like the tidal shredding of a star by a black hole. When a star wanders too close, the intense gravity stretches it into a thin stream of gas, pulling it apart thread by thread. Half of the material falls inward, heating and glowing in a bright flare. The rest escapes into space, joining the interstellar medium. It is a dramatic end, but even here the debris becomes part of the galaxy's future, feeding gas clouds that will later collapse into new stars. Even in the dark spaces between stars, destruction seeds possibility. Shock waves from distant explosions sweep through gas clouds, compressing them just enough to trigger collapse. Magnetic fields twist and reconnect, releasing bursts of energy that stir the surrounding medium. High-energy particles from supernova travel across vast distances, altering the chemistry of young planetary atmospheres. Out of each disturbance comes change, and out of each change the potential for something new. The universe wastes nothing. Every collapse feeds growth. Every loss becomes material for creation. In a cosmos governed by cycles of energy and matter, destruction is not a failure, but a necessary step in the ongoing construction of structure, form, and life itself. And yet, the most surprising truth is this: creation and destruction are inseparable because both are expressions of motion. Nothing in the universe holds still long enough to remain what it once was. Stars grow old, galaxies evolve, planets erode, and even the most stable structures drift toward transformation. What appears permanent is simply in a slow phase of becoming something else. Moments of destruction are not interruptions in the universe's story. They are the punctuation marks that allow the next sentence to begin. The universe does not hurry, yet it is always moving toward something new. Even now, in the quiet sweep of space, the cosmos is unfolding toward futures we can only glimpse through the traces left behind by ancient light. Astronomers watch these faint signals, measuring how galaxies drift apart, how stars age, how the dark fabric of space stretches. From these clues, they try to imagine what will come long after our own era has passed. The future of the universe is not a single path, but a tapestry of possibilities, shaped by forces that work slowly, patiently, across unimaginable spans of time. In the near cosmic future, the night sky will begin to shift. The familiar constellations will stretch and dissolve as stars move along their orbits. Some will drift away unnoticed. Others will flare into brilliance or fade into embers as they exhaust their fuel. The Milky Way will continue gathering small satellite galaxies, pulling them into its halo and blending their stars with its own. Each new addition will subtly alter the galaxy's structure, contributing fresh material for star formation even as older regions grow still. For a time, the universe will remain bustling with the birth and death of stars, each generation adding variety to the galactic landscape. Far ahead, the Milky Way will meet its most significant companion. The nearby Andromeda galaxy is moving toward us, closing the distance bit by bit. When they finally meet, their shapes will distort, stretching into long arcs of stars drawn out by gravity's pull. Over the course of their encounter, their disks will intertwine, and clouds of gas will collide, sparking waves of new star formation. Many stars will pass unharmed through the chaos, gliding along altered paths. The merger will take place so slowly that countless generations could live and vanish without ever seeing the final shape. Eventually, the two galaxies will settle into a single, larger system, bright and rounded, lit by swarms of newborn stars born from the collision's turbulence. As stars continue to form, the universe around them will expand. Space itself is stretching, carrying galaxies away from one another with quiet persistence. The expansion is accelerating, driven by a force that astronomers call dark energy, a mysterious pressure woven into the fabric of space-time. In the far future, this expansion will grow so strong that distant galaxies will slip beyond visibility, their light stretched until it can no longer reach us. Only the nearest cluster will remain bound, a small oasis of stars in an ever-widening dark. To future observers, the universe beyond their local cluster might appear empty, leaving them unaware of the countless galaxies that once filled the sky. Closer to home, stars will continue their cycles of life. Sun-like stars will swell into red giants, shedding their outer layers in luminous shells. Their cores will remain behind as white dwarfs, faint and dense, slowly cooling through the ages. Massive stars will end more dramatically, collapsing into neutron stars or black holes that linger as silent anchors scattered across the galaxy. Planetary systems will shift as their stars evolve, some worlds consumed, others cast outward into cold darkness. A few planets may survive these changes, drifting around the remnants of their stars like quiet reminders of what once was. As time continues its long march, star formation will slow. Gas clouds will be used up, heated, or scattered beyond the reach of collapse. Without fresh material to form new stars, galaxies will gradually dim. The brilliant clusters of young blue stars will fade first, replaced by older, redder populations. The cosmic era of star birth will taper off until only faint flickers remain. The night skies of distant epochs will be calmer, less vibrant, filled with aging stars quietly burning the last of their fuel. In an even more distant future, black holes may become the most important architects of change. Some will merge, sending ripples through space-time that echo across entire galaxies. Others may evaporate slowly through processes predicted by quantum physics, releasing particles in faint whispers until they vanish entirely. These events unfold over timescales so long that they stretch the limits of imagination, far beyond the lifespan of stars, planets, or civilizations. Eventually, the universe may enter an era of cooling. As expansion continues and stars fade, energy will spread thin. Structures that once glowed brightly will fall into long silence. Perhaps the universe will drift toward a state of quiet equilibrium, its contents dispersed, its light redshifted into near-nothingness. Or perhaps new physics will reveal paths we cannot yet see, futures shaped by forces not yet understood. Astronomers explore these possibilities, not because they expect to witness them, but because imagining the future of the cosmos helps illuminate the present. Even in these distant predictions, creation does not disappear. It transforms. Clouds of gas may no longer collapse into stars, but particles may still drift together in rare, quiet places, forming small sparks of structure. Black holes may influence the last fragments of matter, reshaping them in their final moments. The universe may continue evolving long after all familiar processes have ceased, guided by rules we are only beginning to grasp. What lies ahead for the cosmos is a story of change, one written in spans of time far beyond human experience. Yet within it is a kind of peace, a reminder that everything moves through cycles. Galaxies collide and rebuild, stars burn and fade. Space expands and reshapes the stage on which all cosmic events unfold. The future of the universe is vast and unknowable in its details, but its trajectory is a continuation of the same gentle, patient motion that has carried it from its first moments. To look forward is to understand that we live in a chapter of a much greater saga, one that stretches far before us and will continue far beyond. And though our time within it is brief, to glimpse the future of the cosmos is to feel connected to the immense unfolding story of everything that exists. When you look up at the night sky, it is easy to forget how much of the universe you are not seeing. The stars seem countless, scattered like distant lanterns drifting through darkness. yet they are only a faint whisper of what surrounds us. Behind them lie unseen galaxies, hidden clouds of gas, ancient remnants of explosions, and vast currents of energy moving silently through space. We stand on a small planet circling an ordinary star, yet somehow we are part of a story so immense it stretches across billions of years. And in this final moment of reflection, after wandering through cosmic extremes and quiet mysteries, the most astonishing truth is not just what the universe contains, but that we exist within it at all. Across all the phenomena we have explored, from the birth of stars in cold molecular clouds to the death throes of massive suns, from the slow drift of galaxies to the strange forces that bend space itself, one theme rises again and again. The universe is shaped by processes that are both violent and gentle, chaotic and orderly, destructive and creative. It breathes in cycles. It remembers through motion. It evolves through change so slow that only the oldest light can reveal it. And somehow life emerged within these rhythms, tiny and fragile compared to the vastness around it, yet capable of wondering how the cosmos came to be. It is strange to realize that everything you have ever touched, every memory you hold, every breath you take, is built from material forged in stars that lived and died long before Earth formed. The iron in your blood was created in the belly of a giant that collapsed in brilliance. The oxygen in your lungs once drifted through nebulae as simple atoms waiting to join something new. The carbon that shapes every cell in your body passed through explosions and collisions across time. You are woven from the debris of events so ancient and immense that they would have reshaped entire regions of the galaxy. In this way, you are not separate from the cosmos. You are its expression, a brief arrangement of stardust aware of being stardust. And awareness is its own kind of illumination. Stars shine with fusion, galaxies shine with starlight, but living beings shine in a quieter way. We reflect, we question, we imagine. When astronomers point telescopes toward distant galaxies or analyze faint signals carried across billions of years, they are not just gathering information, they are participating in the universe's ongoing act of self-discovery. Through us, the cosmos looks back at itself, trying to understand its origins, its laws, its future. It is a remarkable thought that consciousness, which emerges from atoms arranged in delicate patterns, has grown curious enough to seek answers written in light older than Earth. Our place in all this is both humble and extraordinary. Humble because we occupy a speck of space, a moment in time. Extraordinary because from this small vantage point, we can see so far. Light that began its journey before humans existed now meets our eyes. We map stars that will continue shining long after our civilizations fade. We study galaxies whose collisions will not complete until ages beyond counting. We listen to the faint tremors of space-time created by mergers so distant they happened before our solar system formed. Though our lives are short, our reach extends across unimaginable distances. And while it is natural to feel small in the face of such immensity, smallness does not mean insignificance. A single star is small compared to a galaxy, yet its light can guide travelers across oceans. A single planet is small compared to the void, yet on at least one such planet, life flourished into awareness. You, sitting wherever you are, listening to these reflections, are small compared to the universe, yet you contain the ability to feel awe. That alone connects you to everything we have explored, because awe is the bridge between understanding and wonder. The universe does not ask for our reverence, but it offers moments that inspire it. A nebula glowing softly behind veils of dust, a star collapsing into a brilliant explosion, a comet tracing a luminous arc across the sky. Even the quiet spaces, where matter drifts and time stretches without urgency, remind us that beauty exists in stillness as much as in motion. Each of these scenes is a reminder that the cosmos is not indifferent. It simply follows its nature, unfolding in ways that create structure, energy, and possibility. And in those possibilities, life found its foothold. Perhaps the most meaningful reflection is this: we do not observe the universe from outside. We are inside it, carried along by the same forces that move stars and shape galaxies. Our atoms were forged in its fires. Our thoughts arise from its chemistry. Our curiosity echoes its desire for complexity. To understand the cosmos is, in a sense, to understand ourselves. And so, after wandering through 100 quiet wonders, we arrive back here, on a small orbiting world, with a sky above us that holds more stories than we could ever tell. The universe continues its steady turning. Stars are forming. Light is traveling. Galaxies drift in their ancient spirals. And you are part of this enormous unfolding, a brief but luminous presence in the vastness. If you ever feel lost or overwhelmed, look upward, not for answers, but for perspective. The stars do not solve problems, but they remind us that change is natural, that endings become beginnings, and that even in darkness, something is always moving toward light. You belong to this universe of wonder. You always have.